There are places in the universe so terrifying that they challenge everything we thought we understood about reality. Regions of space where the laws of physics break down, where matter is crushed to infinite density, where radiation tears atoms apart, and where the very fabric of space-time becomes unstable. Some of these places are violent beyond imagination. Others are silent voids that stretch for hundreds of millions of light years, empty and incomprehensible. A few exist at scales so small they defy detection, yet harbour enough destructive potential to erase entire solar systems. If you're ready to explore the darkest, most dangerous corners of the cosmos, hit that like button, because what you're about to discover will fundamentally change how you see the universe. These aren't just curiosities or abstract concepts. These are real places that exist right now, scattered throughout the observable universe, waiting in the darkness. We're going to visit 33 of them. Prepare yourselves. We begin. The Boötes Void is one of the most mysterious and terrifying places in the known universe. Discovered in 1981 by astronomer Robert Kirshner and his team during a redshift survey of galaxies, the Boötes Void is an enormous region of space that is almost entirely empty. Located in the constellation of Boötes, it lies approximately 700 million light-years away from Earth. What makes the Boötes Void so unsettling is its enormous scale and emptiness. Spanning roughly 330 million light-years in diameter, it is one of the largest known voids in the universe. To put that into perspective, if the Milky Way galaxy were placed inside it, it would be alone with no other galaxies visible for hundreds of millions of light-years in every direction. The isolation would be absolute, total, and suffocating. In the entire volume of the Boötes Void, astronomers have found only about 60 galaxies. A region of that size should contain thousands. Think about what this means. Imagine standing on a planet in one of those 60 galaxies, looking up at the night sky and seeing almost nothing. No neighbouring galaxies, no distant clusters of light, just darkness stretching in every direction for distances that dwarf our entire local group of galaxies. You would be living in what amounts to cosmic solitary confinement, cut off from the grand tapestry of the universe by an ocean of nothingness so vast it defies comprehension. The emptiness of the Boötes Void challenges our understanding of the large-scale structure of the cosmos. Scientists believe it formed from gravitational effects early in the universe's history, possibly from the merging of smaller voids as matter clumped together elsewhere, leaving this region behind like a bubble in cosmic foam. But even this explanation feels inadequate when you confront the sheer scale of the emptiness. Some theorists have speculated that such vast emptiness could hint at unknown cosmic phenomena, or that we're seeing the limits of our observational understanding. Could something exist in the void that we simply cannot detect? Could there be forms of matter or energy that don't interact with light, lurking in that darkness? The void's haunting isolation and incomprehensible size make it one of the scariest places in the universe. It's a reminder that the cosmos isn't just filled with stars and galaxies, but also with vast, lonely stretches of absolute nothingness, places where time and light seem to vanish into silence. The Boötes Void exists as a monument to absence, a cathedral of emptiness that shouldn't be possible in a universe supposedly filled with matter and energy. The Eridanus supervoid is one of the most eerie and mysterious structures in the known universe. First identified in 2004 through observations of the cosmic microwave background radiation, the afterglow of the Big Bang, astronomers noticed a strange cold spot in the sky, in the direction of the constellation Eridanus. Further investigation revealed that this region is not just cold, but also vastly underpopulated with galaxies, forming what's now known as the Eridanus supervoid. Located about 1 billion light-years away, this massive cosmic void spans roughly 1 billion light-years across, making it one of the largest known voids in the universe. It is characterized by an extreme lack of galaxies, stars, and matter. But what makes the Eridanus supervoid truly terrifying is its connection to something that shouldn't exist at all. The cosmic microwave background radiation should be almost perfectly uniform across the entire sky, with only tiny fluctuations in temperature. These fluctuations tell us about the early universe, about regions that would eventually form galaxies and clusters. But the cold spot in the direction of Eridanus is far too cold, far too large, and far too empty to be explained by normal cosmic evolution. The temperature difference is only about 70 microkelvins colder than the surrounding space, but across such an enormous area, this represents a statistical anomaly so extreme that it challenges our models of cosmic structure formation. Some scientists believe the supervoid may partially explain the cold spot. As cosmic microwave background photons travel through the void, they lose energy climbing out of its gravitational potential well, a process called the integrated Sachs-Wolf effect. This should make the CMB appear colder in that direction. But even accounting for this effect, the cold spot remains mysteriously colder than it should be. This has led to more exotic theories. Some physicists have speculated that the Eridanus cold spot could be evidence of a collision with another universe, a scar left on our cosmic horizon by a bubble universe that intersected with our own in the first moments after the Big Bang. Others wonder if it represents a topological defect in spacetime itself, a cosmic string or domain wall left over from phase transitions in the early universe. These explanations sound like science fiction, but they're being seriously considered by cosmologists because the alternative, that we simply don't understand how cosmic voids work, is almost as troubling. The Eridanus supervoid exists as a dark monument to our ignorance. Its enormous scale and profound emptiness stir existential dread, reminding us how little we truly understand about the universe. In a cosmos filled with matter, energy, and vibrant galaxies, the Eridanus supervoid is a silent and unsettling exception, a lonely expanse where even light seems to dim and vanish. It's one of the scariest places in the universe precisely because we don't fully know why it exists at all. But cosmic voids aren't just distant curiosities. You live inside one right now. The local void, discovered in 1987, is a vast region of empty space that extends for roughly 150 million light-years and partially surrounds our own Milky Way galaxy. Unlike the Boötes Void, or Eridanus supervoid, which are so distant that they feel abstract, the local void is uncomfortably close. It's part of our cosmic neighbourhood, a reminder that even in our own backyard, the universe harbours vast regions of nothingness. The local void contains fewer than 10% of the galaxies that should exist in a region of its size. Astronomers mapping our local cosmic structure discovered that the Milky Way sits near the edge of this void, positioned on the boundary between emptiness and the more densely populated regions of the Laniakea supercluster. What makes the local void particularly unsettling is that it affects the motion of our galaxy. The void's gravity, or rather its lack of gravity, acts as a cosmic repellent. Dense regions pull galaxies toward them through gravitational attraction, while voids push galaxies away through the absence of that same force. Our galaxy is being influenced by this void right now, its motion through space shaped by hundreds of millions of light-years of nothingness sitting just beyond our galactic neighbourhood. Think about what this means for our cosmic isolation. If you could somehow travel to the centre of the local void and look around, you would see almost nothing in certain directions. The void would swallow your view, presenting darkness where there should be galaxies. You would be standing in a region of space so empty that calling it space almost seems generous. It's more like a wound in the cosmic web, a place where structure failed to form, where the universe forgot to fill in the details. The existence of the local void also raises disturbing questions about our cosmic perspective. For decades, astronomers assumed that our region of the universe was fairly typical, that the density of galaxies around us represented a cosmic average. The discovery of the local void shattered this assumption. We live in a special location on the edge of a massive underdensity. This means that our observations of the universe are biased by our position. When we measure cosmic expansion rates or galaxy distributions, We're doing so from a location that sits next to a vast region of emptiness. How much has this biased our understanding of cosmology? The local void isn't just a scary place, it's a scary truth about our cosmic address. The voids don't end there. In 2013, astronomers discovered something even more disturbing. The KBC void, named after astronomers Ryan Keenan, Amy Barger and Lennox Cowie, is a hypothetical underdensity that might extend for up to 2 billion light-years and could encompass our entire local cosmic region. If the KBC void exists as proposed, then the Milky Way isn't just sitting near the edge of one void. We're inside a nested structure of voids within voids, like Russian dolls made of cosmic emptiness. The evidence for the KBC void comes from observations suggesting that the local universe has a lower matter density than expected from the standard cosmological model. Galaxies in our region seem to be distributed in a way that indicates we're inside a massive underdensity that extends far beyond the local void. This possibility is terrifying because it would mean that our entire cosmological framework might be built on observations made from inside an abnormal region of space. The Hubble constant, the rate at which the universe expands, is measured using nearby galaxies. If those galaxies are inside a giant void where expansion behaves differently, then our measurements might not represent the true cosmic expansion rate. The universe could be expanding faster or slower than we think, simply because we're measuring it from inside a cosmic bubble where the rules are different. The existence of the KBC void remains controversial. Some astronomers argue that the evidence isn't strong enough, that better observations will show our local region is actually typical. But the possibility haunts cosmology like a ghost. What if everything we think we know about cosmic expansion, dark energy, and the ultimate fate of the universe is wrong because we've been observing from inside a cosmic anomaly? The KBC void represents the possibility that our cosmic perspective is fundamentally compromised, that we're like cave dwellers trying to understand the weather by watching shadows on the wall. These voids, vast and empty and incomprehensible, are just the beginning. The universe contains places far more violent, far more extreme, far more hostile to existence itself. Black holes represent perhaps the most terrifying category of cosmic phenomena. They're not just dangerous objects that you should avoid. They're tears in the fabric of reality itself, places where the laws of physics break down, and the universe reveals its capacity for absolute destruction. The event horizon of a black hole is one of the most terrifying frontiers in the universe, a cosmic point of no return. The concept was first developed in the early 20th century following Albert Einstein's theory of general relativity and later refined by physicists like Carl Schwarzschild, who mathematically described the radius around a black hole where nothing can escape, not even light. The event horizon isn't a physical surface but a boundary in space. Once something crosses this invisible line, it is inevitably pulled toward the black hole's centre, or singularity, by immense gravitational forces. No object, no signal, no information can escape past this threshold, meaning anything that falls in is lost to the observable universe forever. Event horizons exist around all black holes, whether they are stellar mass black holes formed from collapsed stars scattered throughout the galaxy, or supermassive black holes lurking at the centres of galaxies. The radius of an event horizon depends on the black hole's mass. For a black hole with the mass of our Sun, the event horizon would be only about 3 kilometers across. For a supermassive black hole containing billions of solar masses, the event horizon can stretch for billions of kilometers, a sphere of no return larger than our entire solar system. What makes the event horizon truly terrifying is what happens to time itself at this boundary. From the perspective of an outside observer, time appears to stop at the edge. If you watched a spacecraft falling toward a black hole, you would see it slow down as it approached the event horizon, becoming redder and dimmer as time dilation became more extreme. The spacecraft would appear to freeze just at the horizon's edge, never quite crossing it, stuck in a moment that lasts forever. But from the perspective of the falling spacecraft, time would pass normally. You would cross the event horizon without any special sensation, without any warning that you've just passed the ultimate boundary. There's no sign, no marker, nothing to indicate that you've entered a region of space from which you can never return. You would look back and still see the universe outside, still see stars and galaxies, though increasingly distorted by the black hole's gravity. You wouldn't realize you're already doomed until you tried to turn around and discovered that every direction points toward the singularity. Up, down, left, right, forward, backward. All directions lead to the same destination. The singularity is no longer in front of you. It's in your future, as unavoidable as tomorrow. This is perhaps the most horrifying aspect of the event horizon. Once crossed, the singularity becomes part of your timeline rather than your space. You can no more avoid reaching it than you can avoid reaching next Tuesday. Time and space have swapped roles inside the event horizon. The singularity isn't a place you're moving toward. It's a moment you're moving toward, an appointment with destruction that cannot be missed or delayed. We've never directly observed an event horizon until 2019, when the Event Horizon Telescope captured the shadow of the one surrounding the supermassive black hole in the galaxy M87, located 53 million light-years away. The image showed a bright ring of radiation swirling around a dark center, the event horizon's silhouette against the glowing accretion disk. That dark patch in the center isn't the black hole itself, it's the shadow of the event horizon, a region where space has been so severely warped that light cannot escape. Looking at that image, you're seeing the edge of the knowable universe, the boundary where information goes to die. The event horizon symbolizes the edge of known physics, a boundary where our understanding breaks down. It's a reminder that the universe harbors places where even light, information, and the laws of nature themselves are erased. But as terrifying as the event horizon is, it's merely the doorway to something far worse. The center of a black hole, known as the singularity, is arguably the most terrifying and mysterious place in the entire universe. While the concept of black holes was first predicted by Albert Einstein's general theory of relativity in 1915, the singularity itself emerged as a key idea in the 1960s through the work of physicists like Roger Penrose and Stephen Hawking. A singularity is a point where matter is crushed into infinite density, and the laws of physics as we know them break down completely. The singularity lies at the very heart of a black hole, hidden beneath the event horizon. From the outside, a black hole may appear as a dark, invisible sphere, but deep within it is the singularity, a place where gravity is so intense that time and space cease to function normally. According to general relativity, all the mass of the black hole is compressed into a single point of zero volume and infinite density. This sounds absurd because it is absurd. Infinity doesn't exist in the physical world. When our equations produce infinite values, it usually means the equations themselves have broken down, that we're trying to describe something that lies beyond the reach of our current theories. Singularities exist all across the universe, typically at the centers of black holes formed by the collapse of massive stars. When a star exhausts its nuclear fuel, its core collapses under its own gravity. If the star is massive enough, nothing can stop this collapse. The core compresses past the point where atoms can exist, past the point where even neutrons can resist the crushing pressure. It collapses into a point, a singularity, and the surrounding space-time warps so severely that an event horizon forms around it. What makes the singularity so frightening is our utter lack of understanding. The laws of physics, including general relativity and quantum mechanics, cannot describe what happens at this point of infinite density. Time, space, and matter become meaningless concepts. It's a cosmic mystery that no human or even light can ever witness directly. The singularity represents the ultimate unknown, a place where the universe turns inside out, where cause and effect break down, where the very concepts of before and after lose meaning. Some physicists speculate that singularities might not actually exist, that quantum effects become important at extremely small scales and prevent the formation of true infinite density. Perhaps the centre of a black hole isn't a point, but rather an incredibly dense but finite region where quantum gravity effects dominate. But we have no theory of quantum gravity, no way to test these ideas, no observations that could confirm or deny these speculations. The singularity remains hidden behind the event horizon, forever shielded from direct observation by the very nature of spacetime itself. If you somehow survived long enough to fall toward a singularity, the experience would be beyond horrific. The process, colourfully named spaghettification, would stretch your body like taffy. The gravitational force on your feet, closer to the singularity, would be enormously stronger than the force on your head, just a metre or two farther away. This tidal force would pull you apart, stretching you into a long, thin strand of atoms, then molecules, then elementary particles. But even this description is too gentle, too organised. As you approach the singularity, these tidal forces would become infinite. You wouldn't just be stretched. You would be torn apart at every scale, from your body down to your organs, your cells, your molecules, your atoms, your subatomic particles, until even the fundamental constituents of matter themselves are ripped into something we have no name for. The singularity is a place where existence itself is erased, where the universe demonstrates its capacity for absolute annihilation. But what if a singularity could exist without an event horizon? Naked singularities are one of the most controversial and terrifying concepts in theoretical physics. According to the cosmic censorship conjecture, proposed by Roger Penrose in 1969, singularities must always be hidden behind event horizons. Nature, the hypothesis suggests, abhors naked singularities and prevents their formation through physical laws we don't yet fully understand. But the cosmic censorship conjecture remains unproven. Mathematical solutions to Einstein's equations exist that describe singularities without event horizons, places where space and time break down but remain visible to the outside universe. If naked singularities exist, they would be the most dangerous objects imaginable. Unlike black hole singularities, which are safely hidden behind event horizons, a naked singularity would be exposed to the universe. You could, in principle, observe it directly, see the place where physics breaks down, where matter has infinite density, and space-time curvature becomes infinite. But observing such an object would be deadly. The gravitational forces near a naked singularity would be just as extreme as those near a black hole singularity, capable of shredding anything that came close. Even more disturbing, naked singularities could violate causality itself. Event horizons protect the universe from the temporal paradoxes that singularities might create. Without that protective barrier, the broken physics at a naked singularity might leak out into normal space-time, creating regions where time loops back on itself, where effects precede causes, where the fundamental order of the universe dissolves into chaos. Some theories suggest that rapidly rotating black holes, if spun fast enough, might shed their event horizons and expose their singularities. These so-called Kerr-naked singularities would rotate at such extreme speeds that centrifugal effects would overwhelm gravity's tendency to form an event horizon. The universe might contain such objects spinning madly in the darkness, places where physics has come undone and reality itself is unravelling. We have no confirmed observations of naked singularities. If they exist, they're extremely rare or well hidden. But the possibility that they might exist, that there might be places in the universe where the breakdown of physics is exposed and visible, is deeply unsettling. It suggests that the universe isn't always careful, that nature's laws might occasionally fail in catastrophic ways. Black holes come in different sizes, from stellar mass objects just a few times heavier than our Sun, to supermassive monsters containing billions of solar masses. But nothing prepares you for TON 618. TON 618 is one of the most terrifying and awe-inspiring objects in the known universe. It is a hyperluminous quasar powered by one of the largest and most massive black holes ever discovered. First identified in the 1950s as a faint blue star during a photographic survey, TON 618's true nature wasn't understood until decades later. In the 1970s, astronomers realised it was not a star but a quasar, a galaxy whose supermassive black hole is actively consuming matter and radiating enormous amounts of energy. What makes TON 618 truly horrifying is the monstrous black hole at its core. Current estimates place its mass at around 66 billion times the mass of our Sun. To put that in perspective, the black hole at the centre of the Milky Way, Sagittarius A star, is only about 4 million solar masses. TON 618's black hole is so massive that it defies conventional models of how such objects form and grow. If you could somehow view TON 618's event horizon, it would span approximately 1,300 astronomical units across. An astronomical unit is the distance from Earth to the Sun, about 150 million kilometres. This means the event horizon of TON 618 would extend 40 times farther than the orbit of Neptune, our solar system's most distant planet. If this black hole replaced the Sun, its event horizon would swallow not just Earth but every planet in our solar system, and reach far beyond them into interstellar space. TON 618 is located 10.4 billion light-years away from Earth, meaning we see it as it existed just a few billion years after the Big Bang. The light from this distant quasar has been travelling through space for most of the age of the universe. Despite this unimaginable distance, its brightness is so intense that it can still be observed from Earth with powerful telescopes. At its peak luminosity, TON 618 was shining with the energy output of 140 trillion suns. To achieve this impossible brightness, the black hole must be consuming matter at a rate equivalent to several hundred solar masses per year. It's eating stars, gas clouds, entire planetary systems, grinding them into superheated plasma that glows with radiation across the entire electromagnetic spectrum. What makes TON 618 so frightening is not just its mass or energy output, but what it represents: the potential for black holes of incomprehensible scale to exist. How did such a monster form so early in the universe's history? Normal black hole growth, through stellar collapse and accretion, shouldn't produce something this massive this quickly. The black hole would have had to grow at the maximum possible rate, consuming matter at the Eddington limit, where radiation pressure from infalling matter nearly equals the inward pull of gravity for almost the entire history of the early universe. Some astronomers speculate that TON 618 might have formed from the direct collapse of enormous gas clouds in the early universe, bypassing the stellar evolution stage entirely. Others wonder if it grew through multiple mergers, absorbing other supermassive black holes over billions of years. The true origin of TON 618 remains mysterious, a puzzle that challenges our understanding of how the most extreme objects in the universe come into existence. If you were somehow transported to a planet orbiting a star near TON 618, the sky would be dominated by a blazing point of light far brighter than any star, bright enough to be painful to look at even from billions of kilometers away. The radiation from the quasar would flood the surrounding space with X-rays and gamma rays, sterilizing any planets within hundreds of light years. Life as we know it could not exist anywhere near TON 618. It is a region of space where the universe's capacity for violence is on full display, where matter is being destroyed on a scale that dwarfs anything we experience in our relatively quiet corner of the cosmos. TON 618 is a reminder that the universe harbours entities so vast and powerful that they challenge our understanding of physics and make us feel infinitely small. But TON 618 isn't the only supermassive monster lurking in deep space. There are other quasars, other supermassive black holes, scattered throughout the universe's distant past. And then there are black holes that have gone rogue, wandering through space like cosmic predators. Rogue black holes are one of the most terrifying phenomena in the universe. Stealthy, invisible destroyers drifting through space with the power to annihilate everything in their path. These black holes are not anchored at the centre of galaxies like supermassive black holes. Instead, they roam the cosmos alone, untethered and undetectable until it's far too late. While black holes themselves have been studied since the early 20th century, the idea of rogue black holes, those not bound to a galaxy, began gaining attention in the early 2000s through simulations and gravitational studies. Rogue black holes are thought to form when massive stars die in supernovae, giving their black hole remnants a kick from asymmetric explosions, or when black holes are violently ejected from galactic centres due to collisions or gravitational interactions. Once free, they drift through interstellar space silently. Since black holes do not emit light, these rogue wanderers are nearly impossible to see unless they interact with matter or distort the space around them. What makes rogue black holes so frightening is their stealth. They could pass through a star system, tear apart planets, or even devour stars, and we might not detect them until the gravitational effects are already happening. It's estimated that there could be millions of rogue black holes drifting through the Milky Way alone. In fact, in 2022, astronomers confirmed a possible detection of a rogue black hole about 5,000 light-years away using gravitational microlensing, a technique where the black hole's gravity bends light from background stars, creating a temporary brightening. Unlike black holes in known locations, rogue black holes could be anywhere, even heading toward us without warning. They're terrifying because they combine the destructive power of black holes with complete unpredictability. If a rogue black hole passed through our solar system, its gravity would disrupt planetary orbits, potentially ejecting Earth into interstellar space or sending it plunging into the sun, and we would have almost no warning. No light, no radiation, no signal, just a gradually increasing gravitational anomaly as an invisible predator approached our cosmic home. They are quite literally death from the dark. Black holes aren't the only stellar remnants capable of extreme violence. Neutron stars, the collapsed cores of massive stars, pack the mass of the Sun into a sphere only about 20 kilometers across. But even among neutron stars, there's a category that stands apart in terms of raw destructive power. Magnetars are neutron stars with magnetic fields so powerful they defy comprehension. The magnetic field strength of a magnetar reaches up to 100 trillion times stronger than Earth's magnetic field. These objects are the strongest magnets in the known universe, and their magnetic fields are so intense that they warp the very atoms around them and can tear apart the fabric of space itself. Magnetars are believed to form from neutron stars that are born with extremely rapid rotation, or from binary neutron star mergers that generate massive magnetic fields during their violent collision. Only about 30 magnetars have been identified in our galaxy, making them relatively rare compared to regular neutron stars and pulsars. What makes magnetars truly terrifying is their unpredictability. Magnetars undergo sudden violent events called starquakes, where their ultra-dense crust fractures under magnetic stress. When this happens, enormous amounts of energy stored in the magnetic field are released in a fraction of a second, creating bursts of X-rays and gamma rays that flood the surrounding space. These bursts can be detected from thousands of light-years away. The most powerful magnetar flare ever recorded occurred in December 2004, from a magnetar designated SGR 1806-20, located about 50,000 light-years from Earth. In just 1/10 of a second, this flare released more energy than the Sun emits in 100,000 years. The burst was so intense that it disrupted Earth's ionosphere and affected satellites, despite the enormous distance. If a magnetar flare of that intensity occurred within just 10 light-years of Earth, it would likely cause a mass extinction event, stripping away our ozone layer and bathing the planet's surface in deadly radiation. The magnetic fields around magnetars are so strong that they affect the quantum vacuum itself. empty space near a magnetar becomes birefringent, meaning it affects light differently depending on the light's polarization, an effect normally seen only in certain crystals. The magnetic field is literally distorting reality, changing how photons behave as they pass through the supposedly empty space around the star. If you could somehow get close to a magnetar, your fate would be sealed long before you reached its surface. At a distance of about 1,000 kilometers, the magnetic field would be strong enough to disrupt the molecular bonds in your body. Your cells would quite literally fall apart as the electromagnetic forces holding your molecules together were overwhelmed by the magnetar's field. Closer still, even atoms would be torn apart, stretched into elongated shapes as the magnetic field becomes powerful enough to affect the electron clouds that give atoms their structure. Magnetars represent the universe's capacity for violence at the smallest scales. They're reminders that even compact objects, things that could fit inside a small city, can harbour enough destructive potential to threaten everything around them for light years in every direction. But magnetars, as violent as they are, pale in comparison to the most energetic events in the universe. Gamma-ray bursts are cosmic catastrophes so powerful that a single event can briefly outshine all the stars in the observable universe combined. Gamma-ray bursts were first detected in the late 1960s by US military satellites designed to detect nuclear weapons tests in space. Scientists were baffled by these mysterious flashes of gamma rays coming from random directions in the sky. It took decades of observations to understand what was causing them. We now know that gamma-ray bursts come in two categories. Short-duration bursts, lasting less than 2 seconds, are thought to result from the collision and merger of two neutron stars, or a neutron star and a black hole. Long-duration bursts, lasting more than 2 seconds, are associated with hypernovae, the deaths of the most massive stars in the universe. When a star, more than about 30 times the mass of our Sun, exhausts its nuclear fuel, its core collapses directly into a black hole. But unlike the relatively sedate collapse of smaller massive stars, these hypergiant stars collapse so violently that they create jets of material moving at nearly the speed of light, punching through the star's outer layers and shooting out into space like cosmic blowtorches. These jets are narrow, only a few degrees wide, but they contain energy equivalent to millions of supernovae focused into twin beams of destruction. If you happen to be looking at a gamma-ray burst from the side, you wouldn't see much, just a bright supernova. But if you were unfortunate enough to be positioned along the jet's axis, you would be hit by a wall of gamma rays and high-energy particles moving at 99.9% of the speed of light. The radiation from a gamma-ray burst is so intense that it would ionize the atmosphere of any planet in its path, stripping away the ozone layer and triggering a cascade of chemical reactions that would poison the air and water. If a gamma-ray burst occurred within our galaxy, and its jet pointed toward Earth, even from thousands of light-years away, it could trigger a mass extinction event. The most distant gamma-ray burst ever detected occurred 13 billion light-years away, a cosmic explosion that happened when the universe was only about 5% of its current age. Despite this incredible distance, the burst was bright enough to be briefly visible from Earth with amateur telescopes. Think about what this means. An explosion occurring nearly at the edge of the observable universe, an event that happened when the first stars were just beginning to form, was luminous enough to be seen across 13 billion light-years of expanding space. The total energy released by a long-duration gamma-ray burst can exceed the energy our Sun will produce over its entire 10 billion-year lifetime, all released in a matter of seconds. This energy doesn't just dissipate harmlessly into space, it propagates outward, interacting with any matter it encounters, ionizing gas clouds, triggering star formation in some regions while sterilizing planets in others. Gamma-ray bursts are the universe's reset buttons, cosmic catastrophes that can erase life from entire regions of a galaxy without warning. Some scientists speculate that a gamma-ray burst might have been responsible for the late Ordovician mass extinction 450 million years ago, when approximately 85% of marine species died out. While this hypothesis remains controversial, it illustrates the potential threat these events pose. A gamma-ray burst within our galaxy, with its jet pointed in our direction, could happen tomorrow. We would have no warning until the gamma rays reached us, travelling at the speed of a light. By the time we detected the burst, it would already be too late. Fortunately, most stars capable of producing gamma-ray bursts are far from Earth, and the odds of a jet pointing directly at us are extremely low. But the possibility exists, a cosmic sword of Damocles hanging over our planet and every other world in the galaxy. Gamma-ray bursts remind us that the universe contains processes so violent that they can affect cosmic evolution across billions of light years, reshaping entire galaxies and determining which regions of space remain hospitable to life. If gamma-ray bursts represent the most energetic explosions in the universe, then Wolf-Rayet stars are the ticking time bombs waiting to produce them. Wolf-Rayet stars are among the most massive, most luminous, and most dangerous stars in the universe. These stellar behemoths have masses ranging from 20 to 265 times that of our Sun, but they're stripped down to their cores, having lost their outer hydrogen envelopes through powerful stellar winds. What remains is a star burning helium and heavier elements, shining with a luminosity up to millions of times brighter than the Sun, and blasting space with winds moving at speeds of up to 2,000 kilometers per second. Wolf-Rayet stars are rare. Only a few hundred are known in our galaxy, but they're impossible to miss when you find them. They sit at the centers of expanding nebulae, carved out by their own stellar winds, surrounded by shells of ejected material glowing with ionized gas. What makes Wolf-Rayet stars terrifying is what they represent. They are stars at the end of their lives, having burned through their nuclear fuel so rapidly that they've stripped themselves bare. Most Wolf-Rayet stars will end their lives as supernovae or hypernovae within a few 100,000 years, a blink of an eye in cosmic terms. Some will produce gamma-ray bursts. These are stars actively preparing to die, and their deaths will be spectacular and destructive. The nearest known Wolf-Rayet star to Earth is WR 124, located about 15,000 light-years away. While this distance is comfortably safe, the star's behaviour is deeply unsettling. It's ejecting mass at a tremendous rate, losing the equivalent of Earth's mass every 10,000 years through stellar winds. The material it expels forms an expanding cloud of glowing gas called a nebula, illuminated by the star's intense ultraviolet radiation. If you could somehow observe a Wolf-Rayet star up close, you would see a star quite literally tearing itself apart. The radiation pressure from fusion reactions in the core is so intense that it drives material off the star's surface at supersonic speeds. The star is eating itself, consuming its own mass to maintain its incredible luminosity, racing toward the moment when its core finally collapses and the star explodes. But Wolf-Rayet stars are dangerous even before they die. Their intense radiation and stellar winds can affect star-forming regions light years away, either triggering new star formation by compressing gas clouds or dispersing those clouds before stars can form. They're cosmic troublemakers, aggressively reshaping their environments, making it difficult for other stars to form nearby. Any planets that might have existed around a Wolf-Rayet star would have been either destroyed or sterilized long ago, their atmospheres stripped away by relentless stellar winds. Wolf-Rayet stars are stellar monsters, beautiful and deadly, burning with such fury that they consume themselves and threaten everything around them. When these monsters finally die, they don't go quietly. Hypernovae are supernova explosions at least 100 times more powerful than normal supernova, releasing enough energy to briefly match the luminosity of an entire galaxy. These explosions occur when the most massive stars, those with cores exceeding 40 solar masses, collapse directly into black holes while simultaneously ejecting their outer layers at relativistic speeds. The core collapse happens so rapidly and violently that it forms jets of matter and energy that punch through the star, creating the conditions for gamma-ray bursts while also tearing the star apart in what astronomers call a collapser. Hypernovae are the birthplace of the heaviest elements in the universe, forging gold, platinum, uranium, and other heavy nuclei through rapid neutron capture processes that occur in the extreme conditions of the explosion. The most famous hypernova occurred 7,500 light-years away and was detected by astronomers in the year 1006. This supernova, now designated SN Thesonu 6, was so bright that it could be seen during the daytime and cast shadows at night. Medieval astronomers recorded it as a new star that remained visible for months. Modern observations of the remnant reveal a shell of debris expanding at 5 million kilometers per hour, still glowing from the energy of the explosion that occurred more than 1,000 years ago. Hypernovae leave behind either black holes or the most massive neutron stars, and they enrich their surrounding regions with heavy elements necessary for planet formation and potentially for life. But their violence also sterilizes vast regions of space. Any planetary systems within hundreds of light years of a hypernova would be bathed in radiation intense enough to strip away atmospheres and extinguish any life that might exist. The surface of a neutron star, whether a regular pulsar, a magnetar, or any other variety, is itself one of the scariest places in the universe. Neutron stars are the remnants of supernova explosions, the crushed cores of stars compressed to densities so extreme that a sugar cube-sized amount of neutron star material would weigh about 1 billion tons. The surface gravity of a neutron star is approximately 200 billion times stronger than Earth's gravity. If you could somehow stand on a neutron star surface, you would weigh as much as a large mountain on Earth. Of course, you couldn't stand on it. The moment you approached, tidal forces would rip you apart. The difference in gravitational pull between your head and your feet, separated by less than 2 meters, would be enough to stretch you into atoms. But let's imagine you could somehow resist these forces and observe the neutron star's surface. What you would see defies description. The surface is incredibly smooth, with variations in height measured in millimeters despite the star's 20-kilometer diameter. This smoothness results from the intense gravity, which crushes any irregularities almost instantly. The surface temperature can range from about 100,000 to 1 million Kelvin, making it glow with X-rays. The star's magnetic field, even for non-magnetars, is about 1 trillion times stronger than Earth's, strong enough to cause strange quantum effects in the space around the star. The neutron star's density creates conditions that don't exist anywhere else in the universe. The outer crust is composed of iron nuclei arranged in a crystal lattice, but as you go deeper, the pressure increases so dramatically that atomic nuclei merge and fall apart, creating exotic states of matter. Deeper still, you reach the outer core, where matter exists as a fluid of neutrons, protons, and electrons. At the very centre, in the inner core, matter might exist in even more exotic forms, possibly as quark matter, where the neutrons themselves break apart into their constituent quarks. We simply don't know. The physics of neutron star interiors remains one of the great unsolved problems in astrophysics. What we do know is that neutron stars represent matter pushed to its absolute limit, compressed as much as possible without collapsing into a black hole. They are testbeds for extreme physics, laboratories where the laws of nature are stretched to breaking point. Beyond individual stellar objects and their remnants, the universe contains structures and phenomena that operate on vastly larger scales. Some of these are mysterious forces that shape the motion of thousands of galaxies. The Great Attractor is one of the most mysterious and unsettling phenomena in the observable universe. It was first discovered in the 1970s and 1980s, when astronomers noticed that our galaxy, the Milky Way, along with hundreds of thousands of other galaxies, We're being pulled toward a specific region of space at immense speeds, roughly 600 kilometers per second. But what was doing the pulling remained hidden, obscured by the dense stars and dust of our own galaxy, in an area called the zone of avoidance. The Great Attractor lies about 150 to 250 million light-years away, in the direction of the constellation Norma, near the centre of the Laniakea supercluster, which includes the Milky Way. Despite its massive influence, it cannot be directly observed with visible light, adding to its eerie allure. It appears to be a gravitational anomaly, an unseen mass exerting a powerful gravitational pull on everything in the region. What makes the Great Attractor so terrifying is not just its invisibility, but also what it implies. There are massive structures in the universe that we cannot see or fully understand, yet they shape the motion of entire galaxies. Later research suggests the Norma cluster, a massive collection of galaxies, is a major component of it. But the full extent of what's behind the Great Attractor's pull remains unknown. Even more unsettling, some scientists believe the Great Attractor may itself be moving toward an even more massive structure called the Shapley supercluster. This implies a cosmic hierarchy of attractors, with larger structures pulling on smaller ones in a chain of gravitational influence that extends across hundreds of millions of light-years. We are being pulled by something that is itself being pulled by something even larger. The universe isn't just expanding, it's also engaged in a complex dance of gravitational attraction, with every galaxy, every cluster, every supercluster tugging on every other structure. The Great Attractor is a reminder that the universe is not only vast and violent, but also filled with unseen forces that tug at everything, including us, drawing entire galaxies into the unknown. Our galaxy is falling towards something we cannot fully see or understand, and there's nothing we can do about it. But the Great Attractor isn't the only mysterious large-scale flow affecting our cosmic neighbourhood. The dark flow is one of the most mysterious and unsettling phenomena in the cosmos, a strange motion of galaxy clusters that defies our understanding of how the universe should behave. It was first detected in 2008 by astronomers using data from NASA's Wilkinson Microwave Anisotropy probe. Researchers noticed that massive clusters of galaxies appeared to be drifting in the same direction, at high speeds toward a specific region of the sky, without any visible cause within our observable universe. This unexplained motion was dubbed dark flow. What makes dark flow so terrifying is that it suggests the presence of something enormous and completely unknown outside the observable universe. Galaxy clusters as far as 2.5 billion light-years away are all being pulled in the same direction, toward a region beyond the edge of what we can see. This hints at the possibility that something exists beyond the known cosmos, perhaps a massive structure or even another universe. The idea that there could be hidden influences beyond the observable universe challenges our understanding of cosmic inflation, the Big Bang, and the very fabric of space-time. Some theories suggest dark flow could be caused by a gravitational pull from a massive structure beyond our cosmic horizon, something we may never be able to observe directly. Other hypotheses propose that dark flow might be evidence of another universe pulling on ours through gravitational interactions that transcend our cosmic boundary. We don't know exactly where the dark flow is coming from, or what's causing it, only that vast numbers of galaxies are being drawn toward a mysterious region of space at speeds exceeding 600 kilometers per second. The dark flow is terrifying because it represents a true unknown, evidence that the universe may be larger, stranger, and more dangerous than we ever imagined. It's like seeing the ripple of a wave and having no idea what caused it, or how big the source might be. The dark flow hypothesis remains controversial. Some astronomers argue that the motion could be explained by structures within the observable universe, that better data analysis will resolve the mystery. But the possibility that something beyond our cosmic horizon is affecting the motion of galaxies in our observable universe is deeply unsettling. It suggests that we are not isolated, that our universe might be subject to influences from realms we cannot see, and may never understand. Closer to home, at the centre of our own Milky Way galaxy, there are phenomena that challenge our understanding. The Fermi bubbles are two enormous structures extending above and below the galactic plane, each spanning about 25,000 light years. Discovered in 2010 by NASA's Fermi Gamma Ray Space Telescope, these bubbles are filled with high-energy gamma rays and appear to originate from the supermassive black hole at the centre of our galaxy, Sagittarius A star. The Fermi bubbles are thought to have formed from a massive outburst of energy from Sagittarius A star, perhaps when it consumed a large amount of matter several million years ago. The energy released inflated these enormous bubbles of hot gas and charged particles, which now extend far above and below the galactic disk. The edges of the bubbles are remarkably sharp, suggesting they formed relatively quickly in a single event, rather than gradually over time. What makes the Fermi bubbles unsettling is what they tell us about our galaxy's violent past. The Milky Way appears relatively quiet today, with its central black hole consuming matter at a slow, steady rate. But the Fermi bubbles are evidence that this wasn't always the case. Millions of years ago, the centre of our galaxy underwent a catastrophic event, powerful enough to launch billion-ton bubbles of material 25,000 light-years into space. Any solar systems near the galactic centre when this occurred would have been sterilized by the intense radiation. Even today, the bubbles continue to emit gamma rays as cosmic rays within them collide with gas molecules. If our solar system were located within one of the bubbles rather than in the galactic disk, Earth would be bathed in high-energy radiation that would make the development of complex life extremely difficult, if not impossible. The Fermi bubbles are a reminder that even our own galaxy, our cosmic home, is capable of violence that could threaten any life within it. But the Fermi bubbles are relatively well understood compared to some theoretical cosmic structures. Cosmic strings are hypothetical one-dimensional defects in space-time, predicted by some theories of the early universe but never observed. If they exist, cosmic strings would be incredibly thin, perhaps narrower than a proton, but they would be incredibly dense and stretch across vast distances, potentially spanning entire galaxies. A cosmic string with the mass of Mount Everest squeezed into a length. The width of the observable universe would create gravitational effects that could alter the paths of light and matter across cosmological scales. Cosmic strings are thought to have formed during phase transitions in the very early universe, moments after the Big Bang when the forces of nature separated from their unified state. As the universe cooled, these defects in space-time might have been left behind like cracks in ice as water freezes. If cosmic strings exist, they would be moving through space at significant fractions of the speed of light. A cosmic string passing through a solar system would gravitationally disrupt planetary orbits, potentially ejecting planets into interstellar space or sending them crashing into their stars. Even more disturbing, cosmic strings might create closed time-like curves, paths through space-time that loop back on themselves, potentially allowing travel backward in time. This would create paradoxes that violate causality, making cosmic strings not just dangerous to physical objects, but dangerous to the logical structure of reality itself. While no cosmic strings have been definitively detected, astronomers continue to search for their signatures. Gravitational lensing observations have looked for the distinctive double-image patterns that a cosmic string would create as it bends light from distant galaxies. Gravitational wave detectors search for the cusps and kinks that would form on oscillating cosmic strings, creating bursts of gravitational radiation. So far, these searches have come up empty, suggesting that if cosmic strings exist, they're either very rare or our current detection methods aren't sensitive enough. But the possibility that these space-time defects might exist, invisible threads capable of disrupting entire star systems and potentially breaking causality, remains deeply unsettling. Even more exotic than cosmic strings are white holes, hypothetical objects that represent the time reverse of black holes. While black holes are regions from which nothing can escape, white holes would be regions into which nothing can enter. Matter and energy would be expelled from white holes, rather than consumed. White holes are mathematical solutions to Einstein's equations of general relativity, but unlike black holes, which we know exist, white holes remain purely theoretical. If white holes existed, they would be extremely unstable. Any matter approaching a white hole would be unable to cross its event horizon in reverse, creating a pileup of material that would quickly convert the white hole into a black hole. This instability suggests that even if white holes formed in the early universe, they would have disappeared almost immediately. But some physicists have speculated that the Big Bang itself might have been a white hole, an object that exploded outward to create our universe. In this scenario, white holes wouldn't exist within our universe, but rather our entire universe would be the interior of a white hole that formed in some higher dimensional space. Other theories suggest that white holes might exist as the opposite ends of wormholes, with matter falling into a black hole emerging from a white hole in another part of the universe, or in another universe entirely. These ideas remain speculative, lacking observational evidence and presenting numerous theoretical problems, but the concept of a white hole, a place that violently expels matter and energy rather than consuming it, is deeply unsettling in its own way. While black holes are terrifying because they destroy everything that falls into them, white holes would be terrifying because they would be cosmic geysers, unpredictable sources of matter and energy erupting into space without warning. Any civilization unfortunate enough to be near a white hole would be constantly bombarded by material ejected from this cosmic fountain, making the region uninhabitable. Returning to objects we know definitely exist, quasar jets are among the most powerful and destructive phenomena in the universe. Quasars are supermassive black holes at the centres of galaxies, actively consuming matter from their surrounding accretion disks. As matter spirals into the black hole, enormous amounts of gravitational potential energy are converted into radiation. But not all of this material falls into the black hole. Some of it is channeled along the black hole's magnetic field lines and expelled in narrow jets moving at nearly the speed of light. These jets can extend for hundreds of thousands of light years, punching through entire galaxies and creating vast lobes of radio emission in intergalactic space. The energy contained in a quasar jet is staggering. A single jet can carry the energy equivalent of billions of stars, focused into a beam just a few light years wide. If Earth were in the path of a quasar jet, even from thousands of light years away, the radiation would be intense enough to sterilize the planet almost instantaneously. Blazars are a special category of quasar where the jet points almost directly at Earth. These objects appear incredibly bright because we're looking straight down the throat of the jet, seeing the full intensity of the radiation being beamed in our direction. Fortunately, all known blazars are millions or billions of light years away, so while they appear bright in our telescopes, the radiation is diluted enough by distance that it poses no threat. But for any civilizations unfortunate enough to be located along the axis of a blazar jet within the same galaxy, the outcome would be catastrophic. The intense radiation would ionize planetary atmospheres, destroy ozone layers, and deliver doses of high-energy particles that would kill any life exposed to them. Quasar jets are cosmic blowtorches, and anything in their path is burned to ash. These jets also play a role in galactic evolution. The energy they deposit into intergalactic space can heat gas to such high temperatures that it cannot cool down and form new stars, effectively shutting down star formation in regions of a galaxy. Astronomers call this AGN feedback, where active galactic nuclei regulate their own growth by preventing new stars from forming in their host galaxies. It's a self-limiting process, but one that dramatically affects the evolution of galaxies throughout the universe. Pulsar wind nebulae represent another category of extreme cosmic environment. Pulsars are rapidly rotating neutron stars that emit beams of radiation from their magnetic poles. As these neutron stars spin, They generate powerful magnetic fields that accelerate charged particles to enormous energies. These particles stream away from the pulsar in a magnetized wind, creating a bubble of high-energy plasma around the star. When this pulsar wind collides with the surrounding material ejected by the supernova that created the pulsar, it forms a pulsar wind nebula, a glowing cloud of synchrotron radiation visible in X-rays and optical light. The most famous pulsar wind nebula is the Crab Nebula, located about 6,500 light-years from Earth. At the center of this expanding cloud of debris sits the Crab Pulsar, a neutron star spinning 30 times per second. The pulsar injects so much energy into the surrounding nebula that the entire structure glows brightly across the electromagnetic spectrum. The Crab Nebula is expanding at about 1,500 kilometers per second, and the pulsar at its heart is gradually slowing down as it converts rotational energy into the kinetic energy of the nebular material. Pulsar wind nebulae are dangerous environments. The high-energy particles within them create intense radiation fields that would be lethal to any biological organism. Even shielded spacecraft would struggle to survive in these environments due to the penetrating nature of the X-rays and gamma rays produced by particle collisions. The Crab Pulsar itself is a fascinating object. Despite being only about 20 kilometers across, it has a magnetic field about 1 trillion times stronger than Earth's, and rotates so fast that points on its equator are moving at about 70,000 kilometers per second, roughly 1/4 of the speed of light. The lighthouse-like beam of radiation it emits sweeps across Earth 30 times every second, creating the pulsing signal that gives pulsars their name. If you could somehow observe the Crab Pulsar up close, you would see a rapidly spinning ball of ultra-dense matter surrounded by a hurricane of charged particles and intense magnetic fields, all glowing with radiation intense enough to be detected across interstellar distances. Some of the universe's most terrifying places involve not just individual objects but cosmic collisions. Colliding galaxies are relatively common in the universe, particularly in galaxy clusters where many galaxies orbit close together. When two galaxies collide, the individual stars rarely hit each other due to the vast spaces between them. But the gas clouds within the galaxies do collide, creating enormous shock waves that compress the gas and trigger massive bursts of star formation. The most famous colliding galaxies visible from Earth are the antennae galaxies, two spiral galaxies that began merging about 1.2 billion years ago. The collision has distorted both galaxies dramatically, pulling out long tidal tails of stars and gas that stretch for hundreds of thousands of light years. At the point where the two galaxies overlap, the collision of their gas clouds has triggered the formation of millions of new stars in giant star-forming regions, much larger than any found in undisturbed galaxies. For any planetary systems caught in these star-forming regions, the environment would be chaotic and deadly. Young massive stars emit intense ultraviolet radiation that can strip away planetary atmospheres. Nearby supernovae would be common as these massive stars rapidly exhaust their fuel and explode. The rate of supernova explosions in vigorously star-forming regions can be thousands of times higher than in normal galaxies, creating a cosmic shooting gallery where deadly radiation floods through space every few hundred years. Our own Milky Way galaxy is on a collision course with the Andromeda Galaxy. The two galaxies are approaching each other at about 110 kilometers per second, and current models predict they will begin merging in approximately 4 billion years. This collision won't destroy Earth directly. The spaces between stars are so vast that the Sun and Earth will likely pass through the merger without colliding with any objects, but the gravitational disruption could eject our solar system from the merged galaxy, sending us hurtling into intergalactic space, or it could push us closer to the galactic center, where radiation levels are much higher and the density of stars increases the chances of gravitational disruptions. The merged galaxy, sometimes called Milkomeda, will eventually settle into an elliptical galaxy quite different from the spiral structure both galaxies possess today. The collision will trigger a burst of star formation as gas clouds in both galaxies collide and compress. This starburst phase will be brief but intense, potentially using up most of the remaining gas in both galaxies and leaving the merged system largely dead, with little material left to form new stars. Any civilizations existing in either galaxy during the merger will witness a dramatic transformation of their cosmic environment. The familiar spiral structure visible in their night skies will be replaced by chaos, with stars, gas clouds, and dust lanes stretched and distorted by gravitational forces. The number of visible galaxies in the night sky will decrease as Andromeda and the Milky Way merge into a single system. These civilizations will be living through one of the most significant events in galactic evolution, a cosmic catastrophe that will reshape their galactic home over hundreds of millions of years. But we don't need to wait billions of years for our galaxy to become dangerous. At the very centre of the Milky Way lurks Sagittarius, a star, a supermassive black hole containing about 4 million times the mass of our Sun. For most of the time, Sagittarius, a star, is relatively quiet, consuming matter at a slow, steady rate. But observations suggest this wasn't always the case, and it won't always remain peaceful. The Fermi bubbles discussed earlier are evidence that Sagittarius A star underwent a massive outburst millions of years ago. Additional evidence comes from observations of glowing clouds of gas near the galactic centre, which appear to be reflecting X-rays from a burst of activity that occurred about 200 years ago. This suggests that Sagittarius A star periodically flares up when it captures and consumes large amounts of matter, perhaps when a star wanders too close, or when a gas cloud falls into the black hole. The region around Sagittarius A star is one of the most extreme environments in our galaxy. Stars orbit the black hole at tremendous speeds. One star, designated S2, completes an orbit around Sagittarius A star every 16 years, reaching speeds of up to 7,650 km per second at its closest approach, about 2.5% of the speed of light. At these speeds and in such intense gravitational fields, relativistic effects become important. The star's motion is measurably affected by general relativity, and observations of its orbit have provided some of the best evidence for Einstein's theory in extreme conditions. Any planets orbiting stars near Sagittarius A star would be subject to incredible tidal forces and intense radiation. The X-ray emission from the hot gas swirling around the black hole would sterilize any worlds within several light years. The density of stars is so high that gravitational interactions would be common, with passing stars regularly disrupting planetary orbits and potentially ejecting planets into interstellar space, or sending them plunging into their suns. Stars that wander too close to Sagittarius, a star, are torn apart by tidal forces in a process called a tidal disruption event. As the star approaches the black hole, the gravitational force on the side facing the black hole becomes much stronger than the force on the far side. This difference in force stretches the star, pulling it into an elongated shape. If the star gets close enough, it's ripped apart completely, with some of its material falling into the black hole while the rest is flung away at high speed. These tidal disruption events create bright flares of radiation as the stellar debris heats up while falling into the black hole. Astronomers have observed several tidal disruption events in other galaxies, and simulations suggest they might occur around Sagittarius A star roughly once every 10,000 to 100,000 years. The galactic centre is a place of incredible violence, where gravity is so strong and matter is so densely packed that catastrophic events are routine. Moving away from galactic centres, the universe contains another category of terrifying objects. Rogue frozen planets are worlds that have been ejected from their parent star systems and now drift through interstellar space in complete darkness. These planets are not bound to any star, receiving no light or heat except the feeble glow of distant stars and the faint warmth left over from their formation. Without a sun, these rogue planets are frozen, with surface temperatures possibly approaching absolute zero. any atmospheres they once had might be frozen solid on their surfaces, creating landscapes of nitrogen ice and methane snow under skies that never see daylight. Scientists estimate there could be billions or even trillions of rogue planets in our galaxy alone, outnumbering stars by a significant margin. Most of these worlds were likely ejected from their star systems through gravitational interactions, perhaps when a passing star disturbed the young planetary system, or through chaotic interactions between planets that resulted in one or more being flung into interstellar space. A few rogue planets have been detected through microlensing, where their gravity bends the light of background stars, causing a temporary brightening that reveals the planet's presence. These observations suggest that rogue planets can range from Earth-sized to many times the mass of Jupiter. Some might even be larger than known planets, massive enough to have retained internal heat from their formation, or from radioactive decay, possibly harbouring subsurface oceans beneath their frozen crusts. The existence of rogue planets is deeply unsettling for several reasons. First, they're nearly impossible to detect unless they happen to pass in front of a background star at just the right moment. The galaxy could be filled with dark, frozen worlds drifting silently through space, and we would never know they were there. Second, a rogue planet passing through our solar system could gravitationally disrupt planetary orbits, potentially ejecting Earth into interstellar space or sending it on a collision course with another planet. The odds of such an encounter are extremely low but not zero. The universe is vast and old, and given enough time, improbable events become inevitable. Third, the existence of so many rogue planets suggests that planetary ejection might be a common outcome of solar system formation. This means that for every stable planetary system like ours, there might be several failed systems, scattered debris fields of orphaned worlds lost to the darkness. The universe might be far more chaotic and violent in its youth than we previously imagined, with stable planetary systems being the exception rather than the rule. Interstellar objects passing through our solar system provide additional evidence of this chaotic universe. In 2017, astronomers detected Oumuamua, the first confirmed interstellar object as it passed through our solar system. Its unusual elongated shape and unexpected acceleration as it left the Sun suggested it might be covered in frozen gases that sublimated and pushed it like a comet, though its exact nature remains debated. In 2019, a second interstellar object, comet 2I Borisov, was discovered. Unlike Oumuamua, Borisov appeared to be a typical comet, with a composition similar to comets from our own solar system. These discoveries confirmed that interstellar objects regularly pass through our solar system, though most probably go undetected due to their small size and high velocity. The existence of interstellar objects raises questions about panspermia, the idea that life or its chemical precursors might be distributed throughout the galaxy by objects travelling between star systems. An interstellar comet could, in principle, carry organic molecules or even microorganisms from one star system to another, potentially seeding planets with the building blocks of life. But interstellar objects could also pose dangers. A large interstellar asteroid passing close to Earth could potentially impact our planet. Unlike asteroids and comets native to our solar system, which we can track and predict years or decades in advance, an interstellar object would appear with little warning, travelling at speeds of tens of kilometers per second relative to the Sun. Even a small interstellar object hitting Earth at such speeds would release enormous amounts of energy, potentially causing regional or even global catastrophes. Another strange category of cosmic object involves stars themselves being orphaned. Orphan stars, also called intergalactic stars or hypervelocity stars, are stars that have been ejected from their host galaxies and now wander through intergalactic space. These stars are moving so fast, typically over 1,000 kilometers per second, that they've escaped the gravitational pull of their home galaxies and will spend the rest of their lives travelling through the vast empty spaces between galaxies. Hypervelocity stars are thought to form through several mechanisms. Some might be ejected through close encounters with a supermassive black hole at the galactic center. In a binary star system that gets too close to the black hole, one star can be captured while the other is flung away at enormous speed. Other hypervelocity stars might result from supernova explosions in binary systems, where the sudden loss of mass when one star explodes can unbind the system and send the surviving star flying away. Astronomers have discovered several hundred hypervelocity stars, though the true number in our galaxy could be much higher. These orphan stars are fascinating because they represent the most extreme outcomes of gravitational interactions in galaxies. Any planets orbiting a hypervelocity star would be in for a strange fate. As the star travels through intergalactic space, the night sky would gradually change. The familiar constellations would slowly shift and distort over millions of years. Eventually, the parent galaxy would shrink to become just another faint smudge among countless others. The intergalactic medium is extremely diffuse, with only about one hydrogen atom per cubic meter on average, so the star wouldn't encounter much material during its journey. But it would be profoundly isolated, light years from the nearest star, in a void between galaxies that could extend for millions of light years in every direction. For any intelligent life on a planet orbiting a hypervelocity star, the realization that they were in intergalactic space, forever cut off from their home galaxy, would be existentially devastating. They would be cosmic exiles, unable to ever return to the galaxy that birthed their star. As we move toward the end of this journey through the universe's scariest places, we encounter phenomena that challenge not just our understanding of specific objects, but our understanding of reality itself. The edge of the observable universe is one of the most mysterious and chilling regions in all of existence. It is the boundary beyond which we can no longer see, simply because the light from those regions hasn't had enough time to reach us since the beginning of the universe. This concept was first understood in the mid-20th century following the discovery of cosmic expansion and the Big Bang theory, which led scientists to realize that the universe has a finite observable limit. The edge isn't a physical wall, but a cosmic horizon, the limit of the visible universe. It lies approximately 46.5 billion light-years away in every direction, farther than the 13.8 billion year age of the universe would suggest, because space itself has been expanding, carrying distant galaxies away from us even as their light travels toward us. What makes this boundary so terrifying is the unknown. Beyond it may lie countless more galaxies, perhaps entirely different laws of physics, alternate universes, or the true scale of the cosmos, none of which we can observe or truly understand. Everything past the edge is forever invisible, cut off by the limits of light and time. Even more unsettling is that galaxies near the edge are moving away so quickly due to cosmic expansion that they will eventually disappear from view forever, leaving us in a darkening universe. Over time, the cosmos will become lonelier and colder as light from distant objects fades into the void. The edge of the observable universe is terrifying because it forces us to confront cosmic isolation, the limits of human perception, and the vast unknown beyond our reach. Is not just a border of space, it's the edge of everything we can ever know. But there's another cosmic horizon that's even more disturbing. The cosmic event horizon represents the boundary beyond which events will never be observable to us, no matter how long we wait. Due to the accelerating expansion of the universe driven by dark energy, galaxies beyond a certain distance are receding from us faster than the speed of light. This means that light leaving those galaxies today will never reach us, no matter how many billions of years pass. The cosmic event horizon is closer than the edge of the observable universe. It lies at approximately 16 billion light-years from Earth. Galaxies beyond this distance are already lost to us. Any light they emit now will be stretched by cosmic expansion faster than it can travel toward us, meaning that light will never arrive. For all practical purposes, these galaxies have crossed a horizon beyond which no communication, no observation, no interaction is possible. They might as well exist in a separate universe. What makes the cosmic event horizon particularly disturbing is that it's shrinking. As the universe continues to expand and the expansion accelerates, the event horizon moves inward, closer to us. Galaxies that are currently observable will eventually cross the event horizon and vanish from view. Given enough time, trillions of years in the future, every galaxy outside our local group will have disappeared beyond the horizon. Future astronomers living trillions of years from now will look up at the night sky and see only the merged remnants of the local group galaxies. They will have no evidence that the billions of other galaxies we see today ever existed. They will have no way to discover the Big Bang or measure cosmic expansion, because all the distant galaxies that allow us to make those measurements will have vanished beyond the horizon. These future astronomers will develop cosmological theories based on a static, eternal universe, because that's all the evidence available to them will support. They will be living in a cosmos that has hidden its own history. This is deeply unsettling because it raises the question of what we might be missing. Are there phenomena that were observable in the distant past, but have already disappeared beyond our cosmic horizon? Have we already lost access to evidence that would revolutionize our understanding of cosmology? The cosmic event horizon is like a slowly closing door, gradually cutting us off from more and more of the universe, eventually leaving us isolated in a small patch of space, unable to see beyond our immediate neighborhood. It's a reminder that our window of opportunity to understand the cosmos is limited. We live in a special time, an era when the universe is old enough for galaxies and stars and planets to have formed, but young enough that we can still see the distant galaxies whose light tells us about cosmic history. We exist in a narrow time window between the chaotic violence of the early universe and the lonely darkness of the far future. This window is closing. Every year that passes, more of the universe slips beyond our cosmic horizon, lost forever. But there's a phenomenon even more terrifying than cosmological horizons. Vacuum decay, also called vacuum metastability event, represents a possible end to everything that exists. This scenario is based on an unsettling possibility in quantum field theory. What if the vacuum state of the universe, the baseline energy level of empty space itself, is not actually at its lowest possible energy? What if we're living in what physicists call a false vacuum, a metastable state that appears stable but isn't the true ground state of the universe? If this is the case, then the universe could undergo a phase transition, suddenly dropping to a lower energy state called the true vacuum. This transition would nucleate at some random point in space, creating a bubble of true vacuum that would expand outward at the speed of light, converting everything it touches. Inside the bubble, the laws of physics would be different. The values of fundamental constants like the mass of electrons, the strength of electromagnetic forces, and the properties of space and time itself would change. Atoms as we know them could not exist in the true vacuum. Any matter caught in the bubble would be instantly torn apart and reconfigured according to the new physics. From outside the bubble, you would see nothing until it reached you. Because the bubble expands at the speed of light, there would be no warning. Light from inside the bubble cannot outrun the boundary to warn you of its approach. The first sign that a vacuum decay bubble was approaching would be the moment it reached you, and by then it would be too late. Everything you are, everything you've ever known would be erased and replaced by a universe governed by different laws. Vacuum decay represents the ultimate cosmic catastrophe, an event that would not just destroy all life and all structure in the universe, but would fundamentally rewrite the rules of reality itself. The new universe that emerged from this phase transition might not even allow for the existence of complex structures like stars, planets, or atoms. It might be a simpler, emptier cosmos, devoid of the richness and complexity that makes our universe interesting. The terrifying aspect of vacuum decay is its randomness. If our vacuum is metastable, the transition to true vacuum could happen at any moment. It might have already started somewhere billions of light years away, with a bubble of altered physics expanding toward us at light speed, invisible and unstoppable. The good news, if it can be called that, is that calculations suggest our vacuum is probably stable or, at worst, extremely long-lived. The metastability timescale, if our vacuum is false, would be many orders of magnitude longer than the current age of the universe. The probability of vacuum decay happening anywhere in the observable universe within the next trillion years is vanishingly small. But it's not zero. The universe is unimaginably vast, and quantum events that are unlikely in any given location become more probable when you consider the entire cosmos over billions of years. Vacuum decay cannot be prevented, cannot be detected before it arrives, and would be absolutely catastrophic. It represents an existential threat not just to life or even to matter, but to the very structure of physical law itself. It's a reminder that even the seemingly stable vacuum of space is not guaranteed to be permanent, that reality itself might be a temporary configuration subject to random collapse. We conclude our tour of the universe's scariest places with a consideration of the ultimate fate of the cosmos. The far future of the universe is not a place in space, but a location in time, yet it is perhaps the most terrifying destination of all. Current cosmological models predict that the universe will continue expanding forever, driven by dark energy. As this expansion continues, galaxies will become more isolated. The Hubble flow will eventually carry all galaxy groups outside the local supercluster beyond the cosmic event horizon, making them forever unobservable. Stars will continue forming for many trillions of years, but gradually the raw materials for star formation will be used up. Hydrogen and helium will be locked away in stars, stellar remnants, or diffuse gas clouds too sparse to collapse under gravity. The era of star formation will end, and the universe will enter a long twilight period dominated by dim red dwarf stars, brown dwarfs, and stellar remnants. Eventually, even the longest-lived stars will exhaust their fuel. The universe will be populated only by white dwarfs, slowly cooling toward absolute zero, neutron stars and black holes that will persist for incomprehensibly long periods. On timescales of 10 to the power of 15 years, roughly 100,000 times the current age of the universe, even these remnants will begin to fade. Proton decay, if it occurs as some theories predict, will cause matter itself to disintegrate. White dwarfs and neutron stars will gradually evaporate as their constituent protons decay into lighter particles and energy. Black holes will be the last structures remaining, but even they are not eternal. Stephen Hawking showed that black holes evaporate through quantum effects, emitting Hawking radiation that slowly carries away their mass. The evaporation time for a black hole increases with its mass. A black hole with the mass of the Sun would take about 10 to the power of 67 years to evaporate. Supermassive black holes like Sagittarius A star would take 10 to the power of 100 years or longer. These timescales are so vast that they lose meaning. They're numbers without reference points, durations that dwarf the current age of the universe as much as the age of the universe dwarfs a human lifetime. But eventually, even the largest black holes will evaporate completely, leaving behind only a bath of low-energy photons and elementary particles spread across an ever-expanding space. This final state, called heat death, is a universe in maximum entropy, where no structure remains, where no energy gradients exist to drive any process, where nothing can happen because everything has already happened. It's a cosmos of perfect equilibrium, completely cold, completely dark, completely dead. This far future is terrifying not because of violence or danger, but because of its utter meaninglessness. It's a universe where all the complexity, all the structure, all the beauty that we see today has been erased by time and entropy. Every star, every planet, every galaxy, every achievement of every civilization that ever existed or will exist, all of it will be ground down by entropy until nothing remains but uniform darkness. The heat death of the universe is the ultimate victory of disorder over order, of simplicity over complexity, of nothingness over being. Some physicists have speculated about possible ways to escape this fate. Perhaps intelligence could survive by somehow harnessing the last dregs of energy as black holes evaporate. Perhaps there are ways to trigger the formation of new universes from quantum vacuum fluctuations, allowing consciousness to hop from dying universe to nascent cosmos. But these scenarios are wildly speculative, based more on hope than on solid physics. The far more likely outcome is that the universe simply runs down, like a clock winding down until its spring is fully unwound and motion ceases forever. We have visited 33 of the scariest places in the universe, vast voids that stretch for hundreds of millions of light years, empty and incomprehensible. Black holes where matter is crushed to infinite density and space-time itself breaks down. Neutron stars so dense that a teaspoon of their material would weigh as much as a mountain. Magnetars with magnetic fields strong enough to disrupt atoms. Gamma-ray bursts that can sterilize entire regions of a galaxy. Cosmic collisions that tear apart galaxies and reshape entire superclusters. Mysterious forces pulling thousands of galaxies toward unknown destinations beyond our cosmic horizon. Rogue objects wandering through space, invisible and unpredictable. And ultimately the slow decay of the universe itself toward a state of maximum entropy and absolute darkness. These places exist. They're not abstractions or thought experiments. They're real locations scattered throughout the cosmos, operating according to the laws of physics, waiting in the darkness. Some are visible in our most powerful telescopes. Others can only be detected through their gravitational effects or their influence on surrounding matter. A few remain purely theoretical, but even these theoretical places are grounded in mathematics and physics, predicted by the same equations that successfully describe the rest of the universe. What makes these places truly terrifying is not just their danger or their violence, but what they reveal about the nature of reality itself. The universe is not a safe place designed for human comfort. It's a vast arena of competing forces, where matter and energy arrange themselves according to mathematical laws that care nothing for life, or consciousness, or purpose. We exist in a small bubble of relative stability, a planet orbiting a star in a quiet corner of a galaxy, protected by our atmosphere and magnetic field from the radiation and cosmic rays that flood through space. Our existence is contingent, precarious, dependent on countless conditions that could change without warning. Yet for all the danger and violence that pervades the cosmos, for all the terrifying places we've explored, the universe has also proven itself capable of extraordinary beauty and complexity. The same laws of physics that create black holes and gamma-ray bursts also create stars, planets, and life. The same entropy that will eventually grind everything to dust has allowed complexity to emerge and flourish for billions of years. We are the universe's way of knowing itself, conscious matter capable of understanding the very laws that govern existence. The scariest places in the universe are also the most informative. They show us the limits of physics, the boundaries where our theories break down and our understanding fails. They challenge us to think more deeply, to develop better theories, to expand our knowledge of how reality operates at its most extreme. Every black hole, every supernova, every cosmic void is a natural laboratory, testing the laws of nature under conditions we could never reproduce on Earth. By studying these extreme environments, we learn not just about those places, but about the fundamental nature of matter, energy, space, and time. The universe doesn't owe us comprehensibility. It doesn't owe us safety or comfort or meaning. It simply exists, vast and ancient and filled with wonders both beautiful and terrible. Our task as conscious beings is not to shrink from this reality, but to embrace it, to explore it, to understand it as deeply as we can during our brief moment of existence. The scariest places in the universe remind us how small we are, how fragile our existence is, how little we truly understand about the cosmos we inhabit. But they also remind us of our capacity for wonder, our ability to reach across cosmic distances with our instruments and our theories, to map the universe and understand its workings despite all obstacles. We may be small, but we are not insignificant. We are the universe attempting to understand itself, and in that attempt lies perhaps the only meaning we'll ever find. Thank you for joining this journey through the cosmos's darkest corners. If you found this exploration compelling, please leave a like and subscribe. The universe contains infinite mysteries, and each one is worth investigating, no matter how terrifying it might be. The scariest places in the universe are also the most fascinating, and they're waiting out there in the darkness, ready to challenge everything we think we know about reality. But the far future and the end of the universe, while philosophically disturbing, feel distant and abstract. Let's return to more immediate dangers, to places in the universe that pose threats not over trillions of years, but right now. The interstellar medium, the space between stars, is often thought of as empty vacuum. But this space is filled with hazards that could prove deadly to any spacecraft attempting interstellar travel, and these same hazards affect the evolution of planets and the possibility of life throughout the galaxy. The interstellar medium consists of gas and dust spread throughout the galaxy at extremely low densities, typically only about 1 atom per cubic centimetre. This seems incredibly sparse compared to Earth's atmosphere, which contains about 10 to the power of 19 molecules per cubic centimetre. But when travelling at high speeds, even this sparse medium becomes dangerous. A spacecraft moving at a significant fraction of the speed of light would encounter these atoms and dust particles with enormous kinetic energy. At relativistic speeds, even individual hydrogen atoms become deadly projectiles. A hydrogen atom hitting a spacecraft travelling at 90% of light speed would impact with the energy of about 100 mega-electron volts, enough to damage molecular structures and create cascades of secondary particles. Travelling through the interstellar medium at high speeds would be like flying through a perpetual sandblast of atomic-scale bullets. The dust component of the interstellar medium poses even greater dangers. Dust grains, tiny particles typically less than a micron across, are scattered throughout interstellar space. These grains consist of various materials including silicates, carbon compounds, and frozen ices. At relativistic speeds, a collision with even a tiny dust grain would be catastrophic. A micron-sized dust grain hitting a spacecraft at half the speed of light would impact with the energy of several tons of TNT. The resulting explosion would vaporize part of the spacecraft and create a shower of high-energy particles that could damage electronic systems and harm any biological organisms on board. This makes interstellar travel at high speeds incredibly challenging. Any spacecraft attempting to reach even nearby stars within reasonable timeframes would need massive shielding to protect against these impacts, adding weight that makes the journey even more difficult. But the interstellar medium doesn't just threaten spacecraft, it also shapes the evolution of planetary systems and determines where life can exist in the galaxy. Regions of dense interstellar medium can strip away planetary atmospheres through ram pressure stripping, particularly affecting planets in orbit around stars moving rapidly through space. Young planetary systems passing through dense molecular clouds might have their outer planets ejected or their cometary populations disrupted, fundamentally altering the architecture of the system. The interstellar medium is also filled with cosmic rays, high-energy particles travelling at nearly the speed of the light. These particles, mostly protons and atomic nuclei, originate from various sources including supernova explosions, pulsar winds, and active galactic nuclei. Cosmic rays flood through the galaxy, creating a background radiation that affects every planet, every star, every object in space. Cosmic rays themselves represent one of the scariest hazards of space travel and one of the ongoing dangers to life throughout the universe. These particles carry enormous energies. The most powerful cosmic rays ever detected have energies exceeding 10 to the power of 20 electron volts, equivalent to the kinetic energy of a baseball thrown at about 90 miles per hour, all concentrated in a single atomic nucleus. When such a particle strikes matter, it creates a cascade of secondary particles, a cosmic ray shower that can affect millions of atoms. For life on Earth, cosmic rays are mostly absorbed by our atmosphere and deflected by our magnetic field. But on planets without thick atmospheres or strong magnetic fields, cosmic rays would constantly bombard the surface, breaking apart complex molecules and making the development of life extremely difficult. Mars, with its thin atmosphere and weak magnetic field, receives much higher cosmic ray doses than Earth, one of many factors that make the Martian surface hostile to life. For astronauts in space or future colonists on other worlds, cosmic rays pose a serious health risk. These high-energy particles can damage DNA, increasing cancer risk and potentially causing acute radiation sickness during intense cosmic ray events. Shielding against cosmic rays is difficult because the particles are so energetic that they can penetrate significant amounts of material. Ironically, very thick shielding can sometimes make the problem worse, as cosmic rays interacting with the shield material can create secondary particle showers that are even more damaging than the original particle. Some cosmic rays have mysterious origins. Ultra-high energy cosmic rays, those with energies above 10 to the power of 18 electron volts, cannot have originated from within our galaxy. At such high energies, interactions with the cosmic microwave background radiation would limit their travel distance to about 160 million light-years, a phenomenon called the GZK cutoff after the physicists who predicted it. This means that ultra-high energy cosmic rays must come from relatively nearby sources in cosmic terms, yet we've been unable to identify specific sources for most of them. Some physicists speculate that the most energetic cosmic rays might result from the decay of exotic particles left over from the Big Bang, or from topological defects in spacetime like cosmic strings. Others suggest they might be accelerated by the jets from supermassive black holes, or by the shock waves from galaxy collisions. The mystery of ultra-high energy cosmic ray origins is deeply unsettling because it means there are acceleration mechanisms in the universe powerful enough to impart energies to individual particles that we cannot replicate or fully explain. Processes that can take an atomic nucleus and accelerate it to speeds so close to the speed of light that the difference becomes meaningless. The universe contains natural particle accelerators far more powerful than anything we could build, and we don't understand how they work. Another category of cosmic danger involves radiation zones around planets and stars. Jupiter's radiation belts represent one of the most dangerous radiation environments in our solar system. The giant planet's powerful magnetic field, about 20,000 times stronger than Earth's, traps high-energy particles, creating radiation belts similar to Earth's Van Allen belts, but far more intense. Near Jupiter's moon, Io, radiation levels are so high that a human without shielding would receive a lethal dose in about 10 minutes. This radiation poses serious challenges for any spacecraft visiting Jupiter's moons. The Galileo spacecraft, which orbited Jupiter from 1995 to 2003, received a total radiation dose equivalent to about 25,000 chest X-rays, gradually degrading its electronics until the mission ended with a controlled plunge into Jupiter's atmosphere to avoid contaminating potentially habitable moons with Earth microbes. Europa, one of Jupiter's moons and a prime target in the search for extraterrestrial life, orbits within Jupiter's intense radiation belts. Any life that might exist in Europa's subsurface ocean would be protected by the moon's ice shell, but the surface is constantly bombarded with radiation that breaks down complex molecules and creates a layer of radiation-processed material. This creates both challenges and opportunities for future Europa missions. The radiation is dangerous for spacecraft and would need to be carefully managed, but the radiation processing of surface ice might also create oxidants that could sink into the subsurface ocean, potentially providing chemical energy that could support life in the dark waters below. Other planets with strong magnetic fields would have similar radiation belts. Exoplanets orbiting close to their stars, called hot Jupiters, might have even more extreme radiation environments. These massive planets orbit so close to their stars that their years last only a few days. The intense stellar radiation and stellar wind would interact with the planet's magnetic field, potentially creating radiation belts, far more intense than Jupiter's. Any moons orbiting such planets would be bathed in deadly radiation. If hot Jupiters have moons, those moons would be among the most hostile environments in the universe, simultaneously cooked by their proximity to the star and irradiated by the planet's radiation belts. The exoplanets themselves represent an entire category of cosmic horror. As we've discovered thousands of planets orbiting other stars, we've learned that the universe is capable of creating worlds far stranger and more hostile than anything in our solar system. Hot Jupiters, massive gas giants orbiting closer to their stars than Mercury orbits our Sun, experience surface temperatures exceeding 2000 Kelvin. At these temperatures, rock vaporizes and metals exist as gases in the atmosphere. Some hot Jupiters are so hot that they have atmospheres made of vaporized iron, silicon, and other metals. These planets might experience weather patterns involving iron rain, where clouds of vaporized metal condense and fall as liquid droplets before evaporating again in the lower atmosphere. The tidal forces on hot Jupiters are immense. The star's gravity pulls more strongly on the side of the planet facing it, creating a tidal bulge. As the planet rotates, this bulge creates friction that dissipates energy as heat, potentially keeping the planet's interior molten. Some hot Jupiters are thought to be spiraling inward toward their stars, doomed to eventually be torn apart and consumed. The atmospheres of these worlds are also being actively stripped away by stellar radiation and stellar wind. Observations have detected extended atmospheres around some hot Jupiters, vast clouds of hydrogen and other gases escaping from the planet and forming comet-like tails streaming away from the star. These planets are quite literally being evaporated, losing mass at rates that will eventually reduce them to rocky cores, orbiting perilously close to their stars. Other exoplanets demonstrate the universe's capacity to create hostile worlds through different mechanisms. Tidally locked planets, where one side always faces their star while the other remains in permanent darkness, would have extreme temperature contrasts. The day side might be hot enough to melt lead while the night side freezes solid. Any atmosphere on such a world would be driven by massive winds as air moves from the hot side to the cold side, creating permanent supersonic hurricanes. Some tidally locked planets might have habitable regions in the twilight zones between eternal day and eternal night, but even these regions would be subject to constant wind and extreme weather as the atmosphere tries to balance the temperature extremes. Water worlds, planets completely covered by deep global oceans with no land above the surface, present their own form of cosmic horror. These worlds might be common in the universe, and at first glance they seem potentially habitable. But the extreme depths of these oceans, potentially hundreds of kilometers deep, would create enormous pressures at the bottom. The water at the base of such an ocean would be compressed into exotic forms of ice that exist only at extreme pressures, ice that is actually hotter than boiling water, but remains solid due to the immense weight of the ocean above it. Life on such a world would be limited to the upper layers of the ocean, where sunlight can penetrate. There would be no shallow seas, no continents, no dry land whatsoever, just endless ocean extending to a seafloor covered in strange high-pressure ice. Iron planets, worlds that lost their outer layers through collisions or were formed in regions depleted of lighter elements, would have surfaces of pure metal. These planets might have iron rain in their atmospheres, where vaporized metal condenses into droplets. The surface would be a landscape of bare metal, possibly molten in regions, reflecting starlight in strange ways. Any visitors to such a world would find an alien landscape unlike anything in our experience. a place where the ground itself is metal, where mountains are made of iron, and where the geology operates according to rules we've never observed. Diamond planets, carbon-rich worlds that formed in regions with high carbon-to-oxygen ratios, might have mantles made of diamond and silicon carbide rather than the silicate rocks familiar from Earth. These worlds would be incredibly hard, with surface materials that could scratch or cut through any known substance. The geology of diamond planets would operate differently from rocky planets, with different types of volcanism and tectonics driven by the unique properties of carbon-based minerals. Some models suggest that diamond planets might have surfaces covered in tar-like substances or oceans of liquid hydrocarbons, creating landscapes that would appear simultaneously alien and strangely organic. Rogue planets, worlds ejected from their star systems and drifting through interstellar space, represent perhaps the most haunting category of exoplanet. These orphan worlds travel through the darkness between stars, receiving no light or heat except the faint glow of distant stars and the cosmic microwave background. Any atmosphere they once had might be frozen solid on their surfaces. If these planets have moons, those moons would orbit in complete darkness, forever frozen. Yet, despite the surface cold, some rogue planets might harbour life. Large rogue planets, particularly those with substantial radioactive elements in their cores, or those that retain heat from their formation, might have liquid water oceans beneath thick shells of ice. These subsurface oceans would be isolated from the universe, warmed from below by geothermal heat, existing in absolute darkness. If life arose in such an ocean, it would be truly alien, evolved in an environment with no star, no seasons, no day-night cycle, nothing except the unchanging darkness and the slow heat from the planet's interior. The existence of rogue planets forces us to reconsider what counts as a habitable environment. We've traditionally thought of habitability in terms of the habitable zone around stars, the region where liquid water can exist on a planet's surface. But if life can exist in subsurface oceans on rogue planets, then habitability becomes almost independent of stars. The galaxy might be filled with wandering worlds hosting hidden biospheres, entire ecosystems evolving in the dark depths of planets that never see a star's light. This is both fascinating and deeply unsettling. It suggests that life might be far more widespread than we imagine, but also far more isolated. Civilizations evolving on rogue planets would have no knowledge of stars or galaxies. Their entire universe would be their planet and its moons. They would have no way to know that they were travelling through interstellar space, no way to observe the larger cosmos. They would be cosmically blind, forever unaware of the universe beyond their tiny isolated world. Some scientists have speculated about sub-brown dwarfs, objects more massive than planets, but not massive enough to sustain fusion-like stars. These objects would emit faint infrared radiation from the heat of their formation and gravitational contraction. A planet orbiting close to a sub-brown dwarf could potentially receive enough heat to maintain liquid water on its surface, creating a strange system where a planet orbits a failed star, and both drift through interstellar space together, a binary system of outcasts wandering between the stars. Such systems, if they exist, would represent the ultimate cosmic isolation, entire solar systems that never belong to any galaxy's stellar population, orphaned worlds orbiting orphaned stars in the vast spaces between galaxies. The cosmic web, the large-scale structure of the universe, is itself a place of danger and mystery. On the larger scales, galaxies are not distributed randomly through space, but form a web-like pattern of filaments, walls, and voids. The filaments are like cosmic highways, streams of galaxies connected by flows of dark matter and gas. The voids are the empty spaces between filaments, vast regions hundreds of millions of light-years across containing few galaxies. This structure formed from the gravitational amplification of tiny density fluctuations in the early universe. Regions that were slightly denser than average attracted more matter, becoming denser still, eventually forming the filaments and clusters we see today. The voids formed where matter was slightly less dense than average, regions that were gradually emptied as their limited matter was pulled toward the growing filaments. Galaxies in filaments experience different evolutionary paths than galaxies in voids. Filament galaxies encounter more neighbours, leading to more frequent gravitational interactions and mergers. The intergalactic gas in filaments is denser and hotter, having been shocked and heated as it fell into the filament structure. This hot gas glows in X-rays and can strip away the gas content of galaxies passing through it, a process called Ram pressure stripping. Galaxies that lose their gas cannot form new stars, gradually fading as their existing stars age and die. The densest regions of the cosmic web, galaxy clusters, are particularly hostile environments for galaxy evolution. These clusters contain hundreds or thousands of galaxies bound together by gravity, all orbiting within a common dark matter halo. The space between galaxies in a cluster is filled with hot intracluster gas, millions of degrees hot, glowing with X-rays. This gas is so hot that it cannot cool down and form stars. Instead, it creates an X-ray emitting atmosphere filling the cluster. Galaxies falling into clusters are stripped of their gas as they plough through this hot intracluster medium. The ram pressure is so strong that it can remove a galaxy's entire gas content in a single pass through the cluster core, a process that takes only a few 100 million years. These stripped galaxies, now devoid of the raw material needed to form new stars, become red and dead, populated only by aging stars with no new stellar generations to replace them as they die. If you lived in a galaxy being stripped of its gas as it fell into a cluster, you would witness a dramatic change in your cosmic environment over millions of years. The spiral arms of your galaxy, regions of active star formation, would gradually fade as the gas was removed. The night sky would become less brilliant as fewer bright young stars formed. Eventually, your galaxy would transform from a vibrant spiral to a dim elliptical or lenticular galaxy. Its star-forming days over, doomed to gradually fade as its stellar population ages. The supercluster scale is where gravity's influence begins to compete with the expansion of space itself. Superclusters are the largest gravitationally bound structures in the universe, collections of galaxy clusters extending for hundreds of millions of light years. The Laniakea supercluster, our cosmic neighbourhood, contains about 100,000 galaxies, including the Milky Way. The entire supercluster is slowly collapsing under its own gravity, with galaxies flowing along the supercluster's internal structure toward regions of higher density. But superclusters are also being torn apart by cosmic expansion. Dark energy, the mysterious force driving the acceleration of cosmic expansion, pulls more strongly on larger scales. While galaxies within a cluster are tightly bound by gravity and will remain together, the space between clusters within a supercluster is expanding. Eventually, this expansion will overwhelm the weak gravitational attraction between clusters, and superclusters will be torn apart, with their component clusters drifting away from each other, isolated islands of galaxies in an increasingly empty universe. This creates a hierarchy of cosmic loneliness. Individual galaxies within clusters will merge over time, eventually forming single giant elliptical galaxies. These merged galaxies will remain bound within their clusters. But the clusters themselves will become increasingly isolated as the space between them expands. Eventually, in the far future, each galaxy cluster will be alone, surrounded by expanding emptiness, unable to see or interact with other clusters. The cosmic web will dissolve, replaced by isolated island universes, each containing a single massive galaxy formed from the merger of all the cluster's member galaxies. This future isolation is built into the current structure of the universe. The same dark energy that is currently accelerating cosmic expansion will continue to separate structures on supercluster scales until nothing remains but isolated galaxy groups, each alone in an expanding void. But even within our current universe, there are structures that demonstrate gravity's power to create extreme environments. The Shapley supercluster, located about 650 million light-years from Earth, is one of the most massive structures in the observable universe. It contains thousands of galaxies organized into dozens of galaxy clusters, all bound together by gravity. The total mass of the Shapley supercluster is estimated at about 10 to the power of 16 solar masses, or 10 quadrillion times the mass of our Sun. This immense concentration of mass creates a gravitational well so deep that it influences the motion of galaxies across a significant fraction of the observable universe. The Great Attractor, discussed earlier, appears to be moving toward the Shapley supercluster, pulled by its enormous gravitational influence. Our local group of galaxies, our galactic cluster, the Virgo cluster, and hundreds of thousands of other galaxies are all being pulled toward Shapley, accelerating through space at hundreds of kilometers per second due to its gravity. What makes the Shapley supercluster particularly terrifying is not just its mass, but its distance and influence. We are being pulled toward a massive concentration of galaxies that is so far away that the light we see from it left when Earth was 650 million years younger, during the Ediacaran period when the most complex life on our planet consisted of strange soft-bodied organisms in ancient seas. The Shapley supercluster has been influencing our motion for billions of years, and will continue to do so for billions more. We are falling toward it at cosmic speeds, and there's nothing we can do about it. Fortunately, cosmic expansion will eventually overcome this gravitational attraction, and will never actually reach Shapley. But the fact that our entire region of the universe is being influenced by a structure so massive and so distant is deeply humbling. Galaxy superclusters are organized by dark matter, the mysterious invisible substance that makes up about 85% of the matter in the universe. Dark matter doesn't interact with light, which is why we cannot see it directly, but it interacts through gravity, and its gravitational effects shape the large-scale structure of the cosmos. Dark matter halos surround galaxies and galaxy clusters, containing far more mass than the visible matter we can observe. These halos extend well beyond the visible boundaries of galaxies, creating vast spheres of invisible matter that dominate the gravitational environment. The Milky Way's dark matter halo, for instance, extends perhaps 600,000 light-years from the galactic centre, far beyond the visible disk of stars which extends only about 50,000 light-years from the centre. Dark matter halos are not uniform. They contain substructure, smaller clumps of dark matter within the larger halo. These sub-halos are remnants of smaller halos that were captured by the larger galaxy's gravity and now orbit within it. Some sub-halos might contain small dwarf galaxies with a few million stars. Others might be entirely dark, containing no stars at all, just clumps of dark matter orbiting invisibly through the galaxy. The Milky Way might contain thousands or even millions of these dark subhalos, most of which we'll never detect because they contain no visible matter. The idea that our galaxy is filled with invisible masses, dark structures that we cannot see but that exert gravitational influence, is deeply unsettling. We're surrounded by things we cannot detect except through their gravity, and we have no way of knowing where they all are or when we might encounter one. If a dark matter subhalo passed through our solar system, would we notice? Possibly, if it was massive enough and passed close enough, it could cause small perturbations in planetary orbits that might be detectable over time. But a smaller subhalo, or one that passed farther away, might leave no detectable trace. We could be sharing our cosmic neighbourhood with dark matter structures we'll never know about, invisible masses that pass through our region of space without interacting with anything except through gravity. This is not science fiction. Dark matter is real, confirmed by multiple lines of evidence including galaxy rotation curves, gravitational lensing observations, and the pattern of temperature fluctuations in the cosmic microwave background. We know dark matter exists and makes up most of the matter in the universe. We just don't know what it's made of or exactly how it's distributed on small scales. Some of the leading candidates for dark matter include weakly interacting massive particles, or WIMPs, hypothetical particles that would interact only through gravity and possibly the weak nuclear force. Another possibility is axions, extremely light particles that would form a kind of quantum wave pervading dark matter halos. More exotic possibilities include primordial black holes that formed in the early universe from direct collapse of dense regions rather than from stellar death, or even something we haven't imagined yet, particles or phenomena completely outside our current theoretical framework. The fact that 85% of the matter in the universe is made of something we don't understand is one of the most profound mysteries in science. We've built a successful cosmological model that explains the evolution and large-scale structure of the universe, but that model depends critically on a component whose nature remains unknown. This uncertainty affects our understanding of cosmic dangers. If dark matter consists of primordial black holes, then the universe contains far more black holes than we currently recognize, scattered throughout every galaxy, invisible unless they actively accrete matter or pass in front of background light sources. If dark matter is made of particles that occasionally interact with normal matter, then we're constantly being bombarded by dark matter particles passing through us and through the Earth, and we simply lack the sensitivity to detect most of these interactions. The universe might be far more populated and far more complex than we realize, filled with dark structures and dark phenomena that we can only glimpse through their gravitational effects. Time itself becomes a hazard at cosmic scales and near extreme gravitational fields. Time dilation, predicted by Einstein's theory of relativity, means that time passes at different rates depending on gravitational potential and relative velocity. Near massive objects, time slows down. An observer near the event horizon of a black hole would experience time passing normally, but to an outside observer they would appear to slow down, their movements becoming more and more sluggish as they approach the horizon, eventually appearing to freeze at the boundary. If you could survive near a black hole's event horizon for what felt like 1 hour to you, decades or centuries might pass in the outside universe. You could potentially use this effect to travel into the future, using the black hole as a time machine, but there would be no way back. The time dilation would be real and irreversible. This creates disturbing scenarios for interstellar travel. If a spacecraft traveled close to the speed of light, relativistic time dilation would mean that time passed more slowly for the crew than for people remaining on Earth. A journey that took 10 years, according to the spacecraft's clocks, might involve 100 years passing on Earth. The travellers would return to find that everyone they knew had aged or died, that their civilization had changed in ways they couldn't predict, that they were strangers in a future that had left them behind. This time, dilation effect increases as you approach the speed of light. At 99.9% of light speed, time dilation factor is about 22, meaning 22 years pass in the outside world for each year experienced by the traveller. At 99.99% of light speed, the factor is about 71. As you get closer and closer to light speed, the time dilation increases without limit, allowing in principle for arbitrarily large jumps into the future. This makes interstellar travel fundamentally asymmetric. You could travel to distant stars, but you would be travelling into their future as well as across space. The faster you travelled, the farther into the future you would go. Any round trip to another star system at relativistic speeds would be a one-way journey through time. You could never return to your own time, only to a future you cannot predict. This creates a form of cosmic exile. Interstellar travellers using relativistic speeds would be cut off from their past, unable to return to the time and people they knew, forever displaced to the future. Each journey would be a leap forward in time, creating a strange existence where the traveller moves through time in discontinuous jumps, each journey isolating them further from their origin point in history. Near black holes, time dilation becomes even more extreme. The film Interstellar dramatized this with a planet orbiting close to a massive black hole, where time passed so slowly that 1 hour on the planet's surface equaled 7 years away from the black hole. While this specific scenario involves some dramatic license, the underlying physics is real. Time dilation near black holes follows precise mathematical relationships, and the effects become arbitrarily large as you approach the event horizon. Just outside the event horizon, time dilation approaches infinity. An observer hovering at this location would experience time almost standing still relative to the distant universe. What felt like moments to them would involve billions or even trillions of years passing in the outside cosmos. They could watch the entire future history of the universe unfold in fast forward, seeing stars die, galaxies merge, and the cosmos expand into its far future state, all while experiencing only brief subjective time themselves. This creates a disturbing possibility. If you fell toward a black hole, but had some way to halt your fall just short of the event horizon, you could become unstuck from time in a sense, existing in a moment that is stretched infinitely from the perspective of the outside universe. You would see the entire future of the cosmos compressed into a finite viewing time, witnessing the heat death of the universe while feeling only minutes pass. Then if you moved slightly farther from the black hole, escaping the most extreme time dilation, you would emerge into a universe unimaginably older than the one you left, all its familiar structures gone, replaced by whatever final state the cosmos achieves. Time dilation near black holes is a doorway to the far future, but it's a one-way door with no possibility of return. Gravitational waves, ripples in space-time produced by accelerating masses, represent another fundamental aspect of cosmic violence. When massive objects like black holes or neutron stars orbit each other, they disturb the fabric of space-time, creating waves that propagate outward at the speed of light. These waves were predicted by Einstein in 1916, but weren't directly detected until 2015, when the LIGO Observatory measured the gravitational waves produced by two merging black holes 1.3 billion light-years away. That detection opened a new window on the universe. Since 2015, dozens of gravitational wave events have been detected, including multiple black hole mergers, neutron star mergers, and possibly even more exotic events. What makes gravitational waves simultaneously fascinating and terrifying is what they reveal about cosmic violence. The first detected gravitational wave event, designated GW150914, was produced by two black holes, each about 30 times the mass of the Sun, spiraling together and merging. In the final fraction of a second before they merged, the two black holes were orbiting each other at about half the speed of light. The collision released more energy than all the stars in the observable universe combined were emitting at that moment, all released in a fraction of a second, all carried away by gravitational waves. This energy output exceeded 10 to the power of 49 joules, an almost incomprehensible number. Yet this titanic event produced gravitational waves that by the time they reached Earth had been weakened by distance to the point where they stretched space by less than 1,000th of the width of a proton. LIGO detected this incredibly tiny distortion, confirming that 1.3 billion years ago, two massive black holes had collided with apocalyptic violence. Subsequent detections have revealed a population of merging black holes more numerous than previously expected. Black hole binaries appear to be common throughout the universe, presumably formed when massive binary stars both undergo supernova explosions and leave behind black holes that remain gravitationally bound. These binary black holes gradually spiral together over millions or billions of years, emitting gravitational waves that carry away energy and angular momentum, causing the orbit to shrink. Eventually, the black holes merge in a violent collision that creates a single larger black hole and releases a burst of gravitational waves. If you were somehow positioned near such a merger, at a safe distance of several thousand astronomical units, you would witness an event beyond description. Two black holes, Each invisible but detectable through their gravitational effects on surrounding light and matter would spiral together at relativistic speeds. The space around them would be severely distorted, creating visual effects as light bends through extreme gravitational fields. At the moment of merger, the two event horizons would touch and combine, forming a single distorted event horizon that would then settle down through a process called ringdown, oscillating like a struck bell as it emits gravitational waves and relaxes to a stable spherical shape. The merger of neutron stars detected for the first time in 2017 in an event designated GW170817 revealed even more information. Unlike black hole mergers, which are invisible except for their gravitational waves, neutron star mergers produce electromagnetic radiation across the spectrum. When two neutron stars collide, the result is a kilonova, an explosion powered by the radioactive decay of heavy elements created in the merger. This particular event, which occurred 130 million light-years away, was detected first by gravitational wave observatories, then seconds later by gamma-ray satellites, and subsequently by optical and radio telescopes. Observations continued for weeks as the kilonova faded and the debris expanded. This single event confirmed several major predictions. It proved that neutron star mergers produce short-duration gamma-ray bursts. It confirmed that neutron star mergers are the primary sites of R-process nucleosynthesis, where the heaviest elements in the universe, including gold, platinum, and uranium, are created. The amount of gold produced in this single merger was estimated at about 10 Earth masses, roughly 200 times the total amount of gold ever mined on Earth, all created in a few seconds of cosmic violence. Neutron star mergers also create dangerous environments for any nearby star systems. The gamma-ray burst produced by the merger would sterilize planets for hundreds of light-years. The kilonova's intense radiation would affect a smaller but still significant region. The gravitational waves themselves, while harmless at cosmological distances, would be intense near the source, literally stretching and squeezing space in oscillating patterns. Any objects within a few hundred astronomical units of the merger would be torn apart by tidal forces before the actual collision occurred, ripped to shreds by the intense and rapidly changing gravitational fields. The universe is full of these mergers happening constantly. Current estimates suggest that several black hole mergers and roughly one neutron star merger occur somewhere in the observable universe every minute. Most of these events happen so far away that the gravitational waves that reach Earth are too weak to detect, even with our most sensitive instruments. But they're happening, an ongoing cosmic violence, black holes and neutron stars colliding throughout the universe in events that release more energy in seconds than stars emit over billions of years. As we continue exploring the universe's most dangerous places, we find phenomena that operate at the boundary between quantum mechanics and general relativity, places where both theories are needed simultaneously, but where they refuse to play nicely together. The Planck scale, at energies around 10 to the power of 19 giga-electron volts and distances around 10 to the power of minus 35 meters, represents the realm where quantum effects and gravitational effects become equally important. At this scale, space-time itself might not be smooth, but rather foamy, with virtual black holes constantly forming and evaporating, with wormholes connecting distant points in space opening and closing, with the very geometry of space fluctuating wildly. We cannot directly observe Planck-scale physics. The energies required are beyond anything we could produce in particle accelerators. The distances involved are smaller than anything we can measure. But theoretical considerations suggest that the Planck scale is where our current theories break down, where new physics must emerge to unify quantum mechanics and gravity. If we could somehow observe space-time at the Planck scale, we might find that space and time are not the smooth continuous fabrics they appear to be at larger scales, but rather grainy, quantized, possibly made of discrete units. String theory suggests that at these scales, the fundamental constituents of matter are not point particles, but tiny vibrating strings, and that space itself has additional dimensions beyond the three we observe, dimensions that are curled up so small that they're only relevant at the Planck scale. Loop quantum gravity, an alternative approach to quantum gravity, suggests that space is made of discrete loops or networks, with areas and volumes quantized in units of the Planck scale. These theories remain highly speculative, lacking experimental confirmation, but they represent serious attempts to understand what happens at the most fundamental level of reality. The Planck scale might be where the universe is truly alien, where the familiar concepts of space and time dissolve into something more fundamental and strange. Black hole singularities exist at the Planck scale or smaller, which is why they're so poorly understood. The singularity at the centre of a black hole is where matter is compressed to infinite density according to general relativity, but quantum effects, which general relativity ignores, must become important before true infinite density is reached. What actually exists at the centre of a black hole remains one of the deepest mysteries in physics. It might be a region of Planck-scale space-time foam. It might be a point where space and time end and something else begins. It might be a doorway to other universes or other regions of our own universe connected by wormholes. Or it might be something even stranger that we lack the conceptual framework to imagine. The early universe, within the first 10 to the power of minus 43 seconds after the Big Bang during the Planck epoch, also involved Planck-scale physics. At that time, the entire observable universe was smaller than the Planck length, and quantum gravitational effects dominated everything. We have no reliable theory that can describe what the universe was like during the Planck epoch. Our understanding of cosmic history begins at the end of this period, roughly 10 to the power of minus 43 seconds after the Big Bang, when the universe had cooled enough that quantum, gravitational effects became less important. Before that moment, our theories fail, and we enter a realm of speculation. The origin of the universe itself, whatever that means, might be forever beyond our understanding because it exists in the Planck regime where our current physics breaks down. Some cosmologists suggest that the Big Bang itself might not have been the beginning, that our universe might have emerged from a previous universe that collapsed and rebounded, or that we exist in an eternally inflating multiverse where Big Bangs happen constantly, creating bubble universes like ours. These ideas remain highly speculative, but they arise from serious attempts to apply quantum mechanics to the universe as a whole. Quantum cosmology is a field fraught with difficulties. How do you apply quantum mechanics to the entire universe when quantum mechanics traditionally involves an outside observer making measurements? If the universe is everything that exists, there is no outside observer. Some physicists argue that the universe exists in a quantum superposition of all possible states until observed, but if no external observer exists, the universe might remain in superposition forever, or alternatively, consciousness itself might play a role in collapsing the cosmic wave function, a suggestion that most physicists find unsatisfying, but that hasn't been definitively ruled out. These fundamental questions about the nature of reality bring us full circle to the nature of cosmic horror. The universe is not just physically dangerous, it's conceptually treacherous. The deeper we probe into cosmic mysteries, the more we discover that our intuitive understanding of reality is inadequate. Space and time are not the fixed stage on which events occur, but are dynamic, flexible, capable of bending, stretching, even ending. Matter and energy are not fundamentally different, but are interchangeable through Einstein's famous equation E equals mc squared. The vacuum is not empty, but seethes with quantum fluctuations that have real physical effects. Particles can tunnel through barriers, exist in superpositions of multiple states simultaneously, and be instantaneously correlated across arbitrary distances through quantum entanglement. The universe revealed by modern physics is deeply strange, operating according to rules that violate our everyday experience and challenge our philosophical assumptions about reality. This strangeness becomes even more apparent when we consider the measurement problem in quantum mechanics. According to the theory, particles exist in superpositions of multiple states until measured, at which point the wave function collapses and the particle takes on a definite value. But what counts as a measurement? What causes the collapse? Different interpretations of quantum mechanics give different answers. The Copenhagen interpretation says measurement causes collapse but doesn't explain what counts as measurement. The many worlds interpretation says the wave function never collapses. Instead, reality splits into multiple branches, each corresponding to a different measurement outcome. In this view, every quantum measurement creates new universes, and we find ourselves in one particular branch while countless other versions of us exist in other branches. The pilot wave interpretation says particles always have definite positions guided by a quantum wave function, avoiding the measurement problem entirely but introducing non-locality, where particles are instantaneously affected by distant events. These interpretations are empirically equivalent. They make the same predictions for all experiments we can perform. The differences are philosophical, matters of how we interpret what the mathematics means about reality. This is deeply unsettling. We have a theory, quantum mechanics, that makes predictions with incredible precision, that has been confirmed by countless experiments, that forms the basis for much of modern technology from semiconductors to lasers. Yet we don't agree on what the theory means about reality. We don't know whether the universe splits into multiple branches, whether the wave function is real or just a calculational tool, whether particles have definite properties before measurement, or whether measurement creates those properties. We can calculate the behavior of quantum systems with extraordinary accuracy, but we don't understand what's really happening. This uncertainty extends to cosmological scales. If quantum mechanics applies to the universe as a whole, and if the many worlds interpretation is correct, then the universe is constantly splitting into inconceivable numbers of branches as quantum measurements occur throughout space. Every quantum event anywhere in the universe creates new branches, new versions of reality. In this view, the universe is not a single cosmos, but an endlessly branching tree of universes, all equally real, all existing in a gigantic quantum multiverse. You exist in all branches where quantum events compatible with your existence occurred. In some branches, Earth was destroyed by an asteroid millions of years ago, and you never existed. In others, quantum fluctuations in the early universe played out differently, and galaxies formed in different configurations. The many worlds interpretation, taken seriously, implies a multiverse of staggering scope, far larger than the observable universe, possibly infinite in extent. Alternatively, if the Copenhagen interpretation is correct and wave functions really do collapse, then something about the process of measurement, of interaction between quantum systems and classical apparatus, causes a fundamental change in reality. The quantum superposition resolves into a single outcome, and the other potential outcomes cease to exist or never existed. This view makes measurement mysterious, a process that seemingly requires conscious observers, or at least macroscopic classical systems, introducing an asymmetry between quantum and classical realms that seems arbitrary. Neither interpretation is fully satisfying, yet one or the other, or some third option must be correct. Reality operates according to rules that we've mathematically characterized but don't fully understand. These foundational uncertainties in physics are mirrored by cosmological mysteries. Dark energy, the force driving the accelerating expansion of the universe, is completely unexplained. We know it exists from observations of distant supernovae and other cosmic measurements, but we don't know what it is. The simplest possibility is that dark energy is a cosmological constant, a property of space itself, where empty space has a fixed energy density that creates repulsive gravity. But if dark energy is a cosmological constant, its value is puzzling. Quantum field theory predicts that vacuum energy, contributions from quantum fluctuations, should be enormous, about 120 orders of magnitude larger than the observed dark energy density. This is the worst prediction in the history of physics, off by a factor of 10 to the power of 120. Something must cancel out almost all of the vacuum energy, leaving only a tiny residual that we observe as dark energy. But we have no idea what could accomplish this cancellation. Alternative explanations suggest dark energy might not be constant, but could vary over time or space, a possibility called quintessence. Or dark energy might be a sign that general relativity breaks down on cosmic scales and needs to be modified. Or we might be wrong about the homogeneity of the universe, and we live in an underdense region where expansion appears to accelerate even without dark energy. Each possibility has problems. Quintessence requires new fields and fine-tuning. Modified gravity faces challenges from observations and theoretical consistency. The idea that we live in a special location violates the cosmological principle. The assumption that the universe is homogeneous on large scales, a principle that has guided cosmology successfully for decades. We're left with a mystery. The universe is accelerating, driven by something we don't understand, toward a future of increasing cosmic isolation and eventual heat death. The combination of dark energy, dark matter, and quantum uncertainty creates a picture of the universe as fundamentally mysterious. We understand about 5% of the universe, the ordinary matter made of atoms. The rest is dark matter and dark energy, substances or properties that we know exist through their effects, but whose nature remains unknown. Even the 5% we do understand operates according to quantum mechanics, a theory we can use with tremendous precision, but whose interpretation remains debated. We are, in a very real sense, cosmically ignorant. We've learned an enormous amount about the universe in the past few centuries, but what we've learned primarily highlights how much we still don't know. This ignorance isn't comfortable. It means the universe could hold surprises, phenomena we haven't discovered because we haven't looked in the right places, or because our current theories blind us to possibilities we haven't imagined. History is full of discoveries that overthrew previous understandings. The universe was thought to be eternal until we discovered cosmic expansion and the Big Bang. Space and time were thought to be absolute until relativity showed they're relative and dynamical. Atoms were thought to be the smallest units of matter until we discovered subatomic particles. Each new discovery opened up new mysteries. The universe keeps revealing itself to be stranger and more complex than we imagined. There's no reason to think this process has ended. We likely haven't discovered all the types of objects or phenomena that exist. There might be forms of matter or energy we've never detected. There might be dimensions or aspects of reality we're completely unaware of because we lack the conceptual framework to even consider them. In this context, the scariest places in the universe might not be the ones we've identified, like black holes and gamma-ray bursts, but rather the ones we haven't discovered yet, the phenomena that exist beyond our current observational reach or outside our current theoretical understanding. The universe might contain dangers we cannot imagine because we don't know enough to imagine them. This is perhaps the deepest form of cosmic horror, the unknown unknowns, the recognition that there might be aspects of reality so alien to our experience that we haven't developed the categories to think about them. We navigate the universe with incomplete maps, using theories that we know are approximations, investigating a cosmos that repeatedly demonstrates its capacity to surprise us. Yet despite all this uncertainty and danger, despite the violence and the vastness and the fundamental strangeness of reality, here we are. Life exists. Consciousness has emerged. We have developed science and technology. We've sent spacecraft beyond our solar system. We've detected gravitational waves from colliding black holes billions of light years away. We've mapped the cosmic microwave background and measured the age and expansion rate of the universe. We've discovered thousands of exoplanets and continue searching for signs of life elsewhere. We exist in an incredibly unlikely pocket of cosmic conditions where complexity can flourish, where entropy gradients allow for the emergence of structure and information, where stars shine long enough for planets to form and life to evolve. Our existence is contingent on countless factors all being just right, yet here we are, conscious matter capable of contemplating the cosmos that created us. The universe is approximately 13.8 billion years old. For most of that time, conditions were hostile to life as we know it. The first few minutes were too hot for atoms to exist. The first few 100,000 years were filled with ionized plasma, opaque to light. The first few 100 million years passed before the first stars formed. Billions of years elapsed as generations of stars lived and died, enriching interstellar space with heavy elements necessary for rocky planets and complex chemistry. Our Sun and solar system formed about 4.6 billion years ago from a cloud of gas and dust enriched by previous stellar generations. Earth formed shortly after and underwent billions of years of geological and biological evolution before complex life emerged, before consciousness arose, before intelligence developed to the point where beings could look out at the cosmos and ask questions about their place in it. We are latecomers to the cosmic story, products of a long chain of events stretching back to the Big Bang. Our moment in cosmic history is special in certain ways. We live in an era when the universe is old enough for complex structures to have formed, but young enough that we can still observe distant galaxies and learn about cosmic history. In the far future, as discussed earlier, cosmic expansion will carry distant galaxies beyond the cosmic event horizon, making them unobservable. Future civilizations will lack the evidence we currently have for the Big Bang and cosmic expansion. They'll be cosmically blind in ways we are not. We live in a golden age of cosmology, a time when the universe is still revealing its history through observable phenomena. This window won't last forever. Eventually the cosmos will become darker, emptier, more isolated. But right now, in this epoch, we can observe and learn and understand. This makes our existence simultaneously insignificant and profound. We are insignificant in scale, tiny creatures on a small planet orbiting an average star in an unremarkable galaxy among trillions of galaxies. Our lives are brief, measured in decades against the billions of years of cosmic history. Our individual actions have no measurable effect on the universe at large, yet we are profound in our capacity for understanding. We are, as far as we know, the only way the universe has to know itself. Consciousness, whatever it is, represents the cosmos becoming aware, matter organizing itself to the point where it can contemplate its own existence and investigate its own nature. Every act of scientific discovery is the universe learning about itself through us. Every moment of wonder as you look up at the night sky is the cosmos admiring its own beauty through your eyes. The scariest places in the universe, the voids and black holes and violent phenomena we've explored, are part of the same cosmos that produced us. They're not separate from us, but part of the larger story, aspects of a universe rich enough and complex enough to contain both destruction and creation, both chaos and order, both the death of stars and the emergence of life. The violence and danger are real. The universe is not safe, but it's also magnificent, operating according to laws we can discover and understand, producing phenomena of staggering beauty and complexity. The fact that we can know any of this, that we can map cosmic structures and measure cosmic expansion and detect gravitational waves from merging black holes billions of light years away, is itself a kind of miracle, an unlikely outcome of natural laws playing out over cosmic time. As we conclude this extended journey through the universe's most dangerous places, we return to the fundamental question of meaning. In a universe this vast and violent, where black holes devour matter, where gamma ray bursts sterilize entire regions of space, where entropy gradually grinds everything to dust, what does anything mean? The universe doesn't appear to have inherent purpose. The laws of physics operate without regard for life or consciousness. Stars burn and galaxies collide according to the same equations that describe the fall of an apple. Nothing in physics suggests that the universe cares whether we exist or not. This can feel nihilistic, the idea that we're cosmic accidents, temporary patterns in matter and energy, doomed to eventually dissolve back into the chaos from which we emerged. But there's another way to look at it. Perhaps meaning isn't something you find in the universe, but something you create within it. The universe provides the stage and the natural laws, but conscious beings create meaning through their choices, their relationships, their understanding, their acts of creation and compassion. You're made of atoms forged in stars, organized into patterns complex enough to think and feel and wonder. The universe has produced something extraordinary through you, not through design or purpose, but through the working out of natural law over billions of years. That's not less meaningful than a universe designed for us. In some ways it's more meaningful because it's real, because it happened without guarantee, because consciousness emerged from purely natural processes without any cosmic insurance policy ensuring it would exist. We are the universe's successful experiment in self-awareness, and that's meaningful precisely because it was so unlikely. The scariest places in the universe remind us how precarious our existence is. We live on a knife edge between being and nothingness, maintained by a delicate balance of forces that could be disrupted in countless ways. A nearby gamma-ray burst, a passing rogue planet, even just the slow increase in our sun's luminosity over geological time, any of these could end our story. But awareness of this precariousness doesn't need to lead to despair. It can lead to appreciation, to wonder, to a determination to make the most of the time we have. The universe is dangerous, yes, but it's also the only place where anything can happen, where stars shine, where planets form, where life emerges and evolves and sometimes becomes conscious enough to understand the cosmos that created it. The dangers and the beauty are inseparable aspects of the same reality. In the end, the scariest thing about the universe might not be any specific place or phenomenon, but rather the totality of what we've learned. The universe is vast beyond human comprehension, ancient beyond human imagination, filled with violence beyond human experience, and operating according to rules that become stranger the more deeply we investigate them. It doesn't care whether we understand it. It doesn't care whether we exist at all. It simply is, unfolding according to mathematical laws that admit no exceptions, creating and destroying with equal indifference. Confronting this reality requires a kind of courage, the courage to accept that we're not the center of the universe, that we're not its purpose, that we're tiny temporary patterns in a cosmos that will outlast us by incomprehensible margins. But it also offers a kind of liberation. If the universe has no inherent meaning, then we're free to create our own. If we're not the purpose of the cosmos, then we can define our own purposes. If we're temporary, then we can make our temporary existence meaningful through our choices and our connections and our efforts to understand. The universe contains 33 types of scary places, perhaps more we haven't yet discovered. But it also contains one type of place, as far as we know, where the universe has become aware of itself. That place is wherever consciousness exists, wherever beings capable of wonder and understanding look out at the cosmos and ask questions about their existence. Right now, for you, that place is wherever you are as you listen to these words. You are a temporary arrangement of atoms, yes, but those atoms are thinking, wondering, trying to understand the nature of the reality they're part of. That's not terrifying. That's extraordinary. The universe has produced something rare and valuable through you, and while that might not have cosmic significance, it has personal significance. You are the universe looking at itself, and in that moment of observation and understanding, meaning emerges, not from the cosmos itself, but from the act of consciousness contemplating existence. Thank you for joining this journey through the universe's scariest places. We've explored voids spanning hundreds of millions of light years, black holes where space-time breaks down, explosions that outshine galaxies, cosmic collisions that reshape space on the larger scales, and the far future when entropy will have erased all structure. These places exist, scattered throughout the cosmos, waiting in the darkness. They're dangerous, mysterious, and profoundly alien. but they're also part of the same universe that produced stars, planets, and life. They're part of your story because you're part of the cosmic story, connected through chains of cause and effect stretching back to the Big Bang. The atoms in your body were forged in stars that died billions of years ago. You're made of ancient starlight and cosmic violence, organised into patterns capable of knowing that you're made of ancient starlight and cosmic violence. That knowledge, that self-awareness, is perhaps the only thing in the universe that could be called miraculous, and it exists in you right now as you contemplate these cosmic mysteries. Sleep well, knowing that despite all the dangers and the vastness and the fundamental strangeness of reality, you exist, you're aware, and for this brief moment in cosmic history, you're part of something unimaginably large and beautiful and terrible. The universe is scary, yes, but you're here to witness it, and that's a privilege that most matter never experiences. The universe imposes fundamental limits on what's possible, not through arbitrary rules, but through the laws of physics themselves. One of the most profound and terrifying of these limits is the impossibility of faster-than-light travel. The speed of light, approximately 300,000 kilometers per second, is not just the speed at which light happens to travel. It's a fundamental limit woven into the structure of spacetime itself. Nothing with mass can reach this speed, and even massless particles like photons cannot exceed it. This limit has profound implications for any species hoping to explore the cosmos. The nearest star system to our Sun, Alpha Centauri, is about 4.2 light-years away. Even travelling at the speed of light, which is impossible for any object with mass, it would take 4.2 years to reach it. More realistically, with conventional rockets, the journey would take tens of thousands of years. With more advanced propulsion systems that might be developed in the future, perhaps nuclear pulse propulsion or antimatter engines, we might reduce this to hundreds or thousands of years, but the journey would still span many human lifetimes. The distances between stars create a fundamental isolation. Our galaxy, the Milky Way, contains perhaps 400 billion stars, but they're spread across a disk 100,000 light-years in diameter. The average distance between stars is about 5 light-years. This means that even if every star had a thriving civilization, those civilizations would be separated by distances that make communication difficult and travel nearly impossible. A radio message sent to Alpha Centauri would take 4.2 years to arrive, and any response would take another 4.2 years to return. That's 8.4 years for a single exchange of information with our nearest stellar neighbours. For more distant stars, delays increase proportionally. A conversation with a civilization 100 light-years away would involve 200 years between sending a message and receiving a response. This isn't just a technological limitation that better technology could overcome. It's a fundamental consequence of physics. The speed of light limit means that the universe is divided into causally disconnected regions, places that cannot affect each other because not enough time has passed for light or any other signal to travel between them. This isolation extends to galactic scales. The nearest large galaxy to the Milky Way is Andromeda, about 2.5 million light-years away. Even travelling at the speed of light, a journey to Andromeda would take 2.5 million years. Any realistic spacecraft travelling at a small fraction of light speed would take tens or hundreds of millions of years to make the journey. This makes intergalactic travel effectively impossible for civilizations like ours. We can observe Andromeda, we can study it with telescopes, but we cannot visit it, cannot communicate with any civilizations that might exist there, cannot affect or be affected by events in that galaxy except through the exchange of light that takes millions of years. The observable universe contains perhaps 2 trillion galaxies, but the vast majority of them are so distant that we'll never be able to visit them or communicate with them. They exist as distant lights in our telescopes, but they're forever beyond our reach. Cosmic expansion makes this isolation worse. Due to the expansion of space driven by dark energy, Distant galaxies are receding from us, and the farther away they are, the faster they're receding. Galaxies beyond a certain distance, currently about 16 billion light-years, are receding faster than the speed of light. This doesn't violate relativity because the galaxies themselves aren't moving through space faster than light. Rather, the space between us and them is expanding faster than light can cross it. Light leaving those galaxies toward us will never arrive because the space it needs to cross is expanding faster than the light can traverse it. These galaxies are beyond the cosmic event horizon, forever unreachable and unobservable. Even galaxies that are currently within our reach won't remain accessible forever. As cosmic expansion accelerates, the cosmic event horizon is slowly moving inward, closer to us. Galaxies that we can currently observe and in principle could reach will eventually cross this horizon and disappear from view. The number of galaxies we could potentially visit or communicate with is constantly decreasing. This creates a profound cosmic loneliness. We are isolated by the vast distances between stars, limited by the speed of light, and gradually losing access to more and more of the universe as expansion carries distant galaxies beyond the cosmic event horizon. The universe is simultaneously full of galaxies and fundamentally empty, filled with light from distant objects, but containing vast spaces that we cannot cross. Think about what this means for the possibility of contact with other civilizations. If intelligent life is common in the universe, there might be millions or billions of civilizations scattered across the cosmos. But the distances between them are so vast that communication is incredibly difficult, and physical contact might be impossible. Each civilization would be isolated, able to observe the universe but unable to reach most of it, sending messages into the void and waiting decades, centuries, or millennia for responses that might never come. Even within our own galaxy, the distances are challenging. If a civilization 1,000 light-years away sent us a radio message today, that message left their world around the year 1024, during Earth's medieval period. By the time we receive the message and respond, they will receive our reply around the year 3024, a millennium in their future. Such exchanges are barely conversations. They're messages in bottles thrown into a vast ocean of space and time. Some scientists have speculated about possible loopholes in the speed of light limit. Wormholes, hypothetical shortcuts through space-time, could in principle connect to distant regions of the universe, allowing travel between them without exceeding the speed of light locally. But creating or maintaining a traversable wormhole would require exotic matter with negative energy density, something that might be impossible to produce in the quantities needed. Even if wormholes exist naturally in the universe, finding them and using them for travel would pose enormous challenges. The Alcubierre drive, a theoretical warp drive that would move a bubble of space-time containing a spacecraft, offers another speculative possibility. This drive wouldn't move the spacecraft through space faster than light. Instead, it would contract space in front of the spacecraft and expand it behind, carrying the spacecraft along with the moving bubble of space-time. But the Alcubierre drive also requires exotic matter and enormous energies, possibly more energy than exists in the observable universe, making it impractical even if theoretically possible. These speculative propulsion methods remain in the realm of theoretical physics, far from any practical application. For the foreseeable future, and probably for much longer, we are confined to slower-than-light travel, isolated by the vast distances between stars and galaxies. This isolation is not necessarily tragic. It means that each world, each star system, each civilization develops in relative safety, protected by distance from cosmic threats. No invading armada can cross interstellar space quickly enough to pose a sudden threat. No galactic empire can expand rapidly enough to dominate the galaxy. The universe's vast scale provides a kind of safety through isolation, ensuring that whatever happens in one region of space takes a very long time to affect other regions. But this safety comes at the cost of loneliness. We are cosmically alone, able to observe the universe but unable to reach most of it. forever separated from other civilizations that might exist by distances that make contact difficult or impossible. This loneliness is built into the structure of the universe through the speed of light limit and cosmic expansion. It's not something technology can overcome, it's a fundamental feature of reality. And it means that our experience of the universe is necessarily limited and local. We can study distant galaxies with telescopes. We can map cosmic structures and measure cosmic expansion. We can even detect gravitational waves from events billions of light years away. But we cannot visit those places, cannot explore them directly, cannot know them except through the ancient light they emit. The universe is simultaneously observable and unreachable, visible but untouchable, knowable through distant observation but unknowable through direct experience. This creates a strange relationship with the cosmos. We're part of it, made of its matter, subject to its laws, but also separated from most of it by unbridgeable distances. We're inside the universe but can only access a tiny fraction of it, the small region of space within our cosmic neighbourhood, and the ancient light from distant regions whose sources have long since changed or disappeared. The nature of time at cosmic scales adds another layer of strangeness to our cosmic isolation. When we observe distant objects, we're not seeing them as they are now, but as they were when their light began its journey toward us. The sun we see in the sky is not the sun as it exists right now, but as it was 8 minutes ago when its light left the solar surface. The nearest star, Proxima Centauri, appears to us as it was 4.2 years ago. Distant galaxies appear as they were millions or billions of years ago. The farther we look into space, the deeper we look into the past. The most distant galaxies observable with powerful telescopes appear as they were more than 13 billion years ago, when the universe was young and those galaxies were just forming. Those galaxies, as they appear to us, no longer exist in that form. They've evolved, merged with other galaxies, changed in ways we cannot observe, because the light carrying information about their current state hasn't reached us yet and won't for billions of years. This creates a fundamental disconnection between observation and reality. Every object we observe in the night sky exists at a different moment in time. The stars we see are scattered across thousands of years of history. Some of those stars might have already died, but their light continues travelling toward us, and we won't know they're gone until their dying light reaches us, perhaps centuries from now. We live in a universe where the present moment is unknowable, except for our immediate vicinity. Everything beyond our local region exists for us only as historical records, ancient light carrying information about how things were, not how they are. This makes the universe simultaneously observable and mysterious. We can study cosmic history through observation, seeing galaxies in various stages of evolution, but we cannot know the present state of distant regions. The universe's present moment is hidden from us by the finite speed of light and the vast distances between objects. Philosophers have contemplated whether it's meaningful to speak of a universal present moment at all. Relativity tells us that simultaneity is relative, that observers in different reference frames will disagree about which events are simultaneous. There's no absolute universal clock ticking the same time everywhere in the cosmos. Time itself is relative, dependent on motion and gravitational fields. This means the question of what the universe looks like right now doesn't have a well-defined answer. Right now relative to what? To us here on Earth, the universe appears one way, with distant galaxies as they were in the distant past. To an observer in a different galaxy or moving at a different velocity, the universe would appear differently. The present moment is not a cosmic universal, but a local phenomenon, defined relative to an observer's specific location and motion. This relativity of time creates a kind of cosmic solipsism. Each observer has their own present moment, their own definition of now, and these presents don't necessarily agree with each other, except in the local region, where relativistic effects are negligible. Time dilation adds further strangeness. Near massive objects or at high velocities, time passes at different rates. An astronaut orbiting a black hole at a safe distance but in a strong gravitational field would experience time passing more slowly than someone far from the black hole. What feels like 1 hour to the astronaut might correspond to several hours passing for the distant observer. Both experiences are real. Time genuinely passes at different rates in different circumstances. This isn't an illusion or a measurement artifact. It's a fundamental feature of how time works in our universe. Time is not a fixed, absolute background against which events occur. It's a dimension of space-time that can stretch, compress, and even come to an end in extreme conditions. Near a black hole's event horizon, time dilation approaches infinity. At the event horizon itself, time appears to stop from the perspective of an outside observer. Inside the event horizon, time and space exchange roles, with the singularity becoming a moment in the future rather than a location in space. These features of time create profound questions about the nature of reality. If time passes at different rates in different circumstances, if there's no universal present moment, if the past and future have an ambiguous relationship near black holes and other extreme objects, then what does it mean for something to exist? Does an object that's currently beyond our cosmic event horizon exist, even though we can never observe it or interact with it? Does the future exist in some sense, or is it yet to be determined? Does the past still exist somewhere, or has it been replaced by the present? Physics doesn't provide clear answers to these questions. The mathematics of relativity and quantum mechanics describe how things behave but remain neutral about questions of existence and reality. We're left to interpret the equations, to decide what they mean about the nature of time and being. Some physicists following the block universe interpretation of relativity argue that all moments in time exist equally, that the past, present and future are all real, and the distinction between them is a psychological illusion. In this view, the universe is a four-dimensional block of space-time containing all events that ever happen, with your entire life existing as a world line threading through this block. You experience time flowing because your consciousness moves along this world line, experiencing different moments sequentially, but all the moments exist simultaneously in the block. Other physicists reject this view, arguing that the present moment is special, that only the present exists while the past no longer exists and the future doesn't exist yet. In this presentist view, time genuinely flows, with new moments coming into existence as old moments cease to exist. The debate continues, with no clear experimental way to distinguish between these interpretations. What's undeniable is that time is strange at cosmic scales. The universe has existed for 13.8 billion years, but this time frame is measured in our reference frame relative to our motion and gravitational environment. In other reference frames, particularly those involving extreme velocities or strong gravitational fields, different amounts of time have passed. The universe doesn't have a single age that all observers would agree on. It has a range of ages depending on the observer's circumstances. This is deeply weird. We're accustomed to thinking of time as universal and absolute, a cosmic clock that ticks the same everywhere. But the universe doesn't work that way. Time is local, relative, dependent on circumstances. The cosmic clock ticks at different rates in different places. Against this backdrop of cosmic isolation, relativistic time, and vast distances, stars continue their slow evolution according to nuclear physics and gravity. Stellar evolution operates on timescales that dwarf human history. The smallest stars, red dwarfs with masses less than about 40% of the Sun's mass, burn hydrogen so slowly that they can remain on the main sequence for trillions of years. The smallest red dwarfs might have lifetimes exceeding 10 trillion years, far longer than the current age of the universe. These stars will outlast all others, still shining faintly long after more massive stars have exhausted their fuel and died. As the universe ages and star formation gradually ceases, red dwarfs will dominate, the last stellar embers in a darkening cosmos. Red dwarfs are common, comprising about 75% of all stars in the universe. Despite their abundance, none are visible to the naked eye from Earth because they're so dim. The nearest star to our solar system, Proxima Centauri, is a red dwarf. It's only 4.2 light-years away, yet it's too faint to see, without a telescope. Red dwarfs are M-class stars with surface temperatures of only about 2000 to 3500 Kelvin, much cooler than our Sun's 5800 Kelvin surface temperature. They shine mostly in infrared wavelengths, appearing as dim red or orange points of light if you could observe them up close. Planets orbiting in the habitable zones of red dwarfs, where liquid water could exist, would need to orbit very close to their stars, often closer than Mercury orbits our Sun. This proximity creates challenges for habitability. The planets would likely be tidally locked, with one side always facing the star and the other in permanent darkness. The star side would be hot while the night side would be frozen, with only a narrow twilight zone potentially offering temperate conditions. Red dwarfs are also prone to stellar flares, sudden releases of magnetic energy that temporarily brighten the star and flood the surrounding space with radiation. These flares can be enormous relative to the star's normal output, sometimes increasing the star's brightness by 10% or more for hours or days. For planets orbiting close to red dwarfs, these flares would deliver intense doses of ultraviolet and X-ray radiation, potentially stripping away atmospheres over time. Despite these challenges, red dwarfs remain intriguing targets in the search for habitable worlds because they're so common and long-lived. If life can adapt to the conditions around red dwarfs, then habitable environments might be abundant in the universe, potentially persisting for trillions of years as red dwarfs slowly consume their hydrogen fuel. Eventually, even red dwarfs will exhaust their hydrogen. When this happens, these stars will transition to burning helium, swelling slightly and becoming white dwarfs, stellar remnants composed of degenerate matter supported by electron degeneracy pressure. White dwarfs are incredibly dense. A white dwarf with the mass of the Sun would be about the size of Earth. A teaspoon of white dwarf material would weigh several tons. The electrons in this matter are packed so tightly that quantum mechanical pressure prevents further compression. This pressure doesn't depend on temperature, so white dwarfs can cool down over enormous timescales without collapsing further. A newly formed white dwarf can have a surface temperature exceeding 100,000 Kelvin, glowing brilliantly in blue-white light. But white dwarfs don't generate new energy through fusion. They simply radiate away the thermal energy they contain, gradually cooling over billions of years. The cooling sequence of a white dwarf is predictable and slow. A white dwarf cools from 100,000 Kelvin to about 10,000 Kelvin in about 1 billion years, fading from blue-white to yellow to red. As it continues cooling below 10,000 Kelvin, it becomes dimmer and redder, eventually emitting most of its radiation in infrared wavelengths. After about 10 billion years, roughly the current age of the universe, a white dwarf might cool to about 5,000 Kelvin, similar to the surface temperature of a red dwarf but much dimmer because of its small size. The cooling continues inexorably. After 100 billion years, the white dwarf would be cold and dim, perhaps 3,000 Kelvin, emitting a faint red glow. After 1 trillion years, it would be nearly black, cooled to perhaps 1,000 Kelvin, barely glowing at all. After 10 trillion years, it would be essentially cold, close to the temperature of the cosmic microwave background, which is itself cooling as the universe expands. At this point, the white dwarf would be a black dwarf, a stellar corpse that has cooled to near absolute zero, no longer emitting significant radiation, invisible except through its gravitational effects. No black dwarfs exist yet in the universe, because the universe isn't old enough. The coolest white dwarfs observed have temperatures around 3,000 to 4,000 Kelvin, still far from the complete cooling required to become black dwarfs. But given enough time, all white dwarfs will become black dwarfs, cold stellar corpses drifting through space. These black dwarfs will be among the last remnants of stellar evolution, persisting long after all the stars have died and all the black holes have evaporated. They'll exist as dark monuments to the stellar era, balls of degenerate matter slowly cooling toward absolute zero, orbited perhaps by the frozen remains of planets that once basked in their heat. The universe will be filled with these invisible objects, dark remnants of stars that once shone, now cold and silent, contributing nothing to the cosmos except their gravitational presence. Some white dwarfs have more dramatic fates. White dwarfs in binary systems can accrete matter from companion stars. If enough matter falls onto the white dwarf to push its mass above about 1.4 solar masses, the Chandrasekhar limit, electron degeneracy pressure can no longer support it. The white dwarf collapses catastrophically, and the increase in pressure and temperature triggers a runaway thermonuclear explosion that destroys the entire star. This is a Type Ia supernova, an explosion so bright that it can briefly outshine an entire galaxy. Type Ia supernovae are remarkably uniform in brightness, because they always result from white dwarfs reaching the same mass limit. This uniformity makes them useful as standard candles in cosmology. By measuring how bright a Type Ia supernova appears and comparing it to its known intrinsic brightness, astronomers can calculate its distance. Observations of distant Type Klein Ia supernova in the late 1990s revealed that the universe's expansion is accelerating, leading to the discovery of dark energy and a Nobel Prize for the astronomers who make the observation. But for most white dwarfs, the fate is not explosive but simply cold. They'll cool slowly, radiating their heat away over incomprehensible timescales, eventually becoming black dwarfs that persist in the darkness. These cooling remnants will be joined by neutron stars, even denser stellar remnants left behind by supernova explosions of more massive stars. Neutron stars have similar cooling trajectories, but start from higher initial temperatures and cool more slowly due to their greater mass and density. A newly formed neutron star might have an internal temperature of billions of degrees, hot enough that neutrinos produced in the interior can escape, carrying away energy and cooling the star. Over the first few thousand years, neutrino cooling dominates, rapidly reducing the star's temperature. After neutrino cooling becomes inefficient, the neutron star cools through photon emission from its surface, a much slower process. After 1 million years, a neutron star might have a surface temperature of about 1 million Kelvin, still incredibly hot but much cooler than its birth temperature. After 100 million years, the surface might cool to 100,000 Kelvin. The cooling continues, slowing over time, with the neutron star temperature decreasing logarithmically rather than linearly. Neutron stars, like white dwarfs, will eventually cool to near absolute zero, becoming black neutron stars, invisible unless they're accreting matter or unless their magnetic fields create detectable effects. But this cooling takes far longer than the current age of the universe. Even ancient neutron stars formed billions of years ago are still relatively warm by cosmic standards, with surface temperatures potentially in the tens of thousands of Kelvin. The coldest neutron stars we've observed still emit detectable X-rays, indicating temperatures exceeding 100,000 Kelvin. It will take trillions of years for neutron stars to cool to the point where they're truly cold, no longer emitting significant radiation. But eventually this too will happen. The universe will be populated by cold stellar remnants, white dwarfs and neutron stars that have cooled to near absolute zero, along with black holes that continue to exist, slowly evaporating through Hawking radiation on even longer timescales. Imagine the far future universe, trillions of years from now, after star formation has ceased and the last stars have died. The cosmos would be dominated by these stellar remnants, cold and dark, along with an ever-decreasing population of long-lived red dwarfs that continue to burn through their hydrogen fuel. Galaxies would be dark, their light coming only from these feeble red dwarfs, and perhaps from the occasional white dwarf that has accreted enough matter to undergo a nova, briefly flaring up before settling back into darkness. The universe would be a far lonelier place than it is now, with far less light, far less energy, far less activity. The grand cosmic drama of stellar birth and death would have mostly played out, leaving behind only the debris, the cooling remnants of stars that once burned bright. But even in this dark future, structure would persist. Galaxies would still exist, held together by gravity and by their dark matter halos. Planets would still orbit their dead stars, frozen worlds circling cold stellar corpses. Potentially, life might still exist in certain locations. Planets with substantial internal heat from radioactive decay or tidal heating might maintain subsurface oceans for trillions of years, habitable environments isolated from the cold darkness outside. Civilizations advanced enough to harness the dwindling energy available might persist, living around the last stars or perhaps deriving energy from black holes through careful manipulation of their accretion disks or through the Penrose process, extracting rotational energy from rotating black holes. These civilizations would exist in a profoundly different universe than the one we inhabit, a cosmos that has exhausted most of its usable energy, where resources are scarce and survival requires extraordinary efficiency. Science fiction has explored these far future scenarios, imagining civilizations that must make do with the meagre energy available in a cooling universe. They might harvest the last dregs of energy from evaporating black holes, or from matter slowly falling into black holes. They might slow their metabolic and computational processes to conserve energy, effectively time-dilating their consciousness so that subjective experience continues even as objective time stretches over astronomical durations. In a universe approaching heat death, life and intelligence might persist in forms we wouldn't recognize, adapted to conditions of extreme cold and energy scarcity, thinking thoughts at rates millions of times slower than biological thought, experiencing time in ways utterly alien to our experience. Or perhaps life cannot persist in such conditions, and the far future universe will be genuinely lifeless, a realm of dead matter and cold stellar remnants slowly decaying toward maximum entropy. The concept of entropy connects to the ultimate fate of all cosmic structures. Entropy, roughly speaking, is a measure of disorder or randomness in a system. The second law of thermodynamics states that entropy always increases in closed systems, meaning that disorder gradually increases over time. This law applies to the universe as a whole. The cosmos started in a highly ordered state at the Big Bang, with matter and energy distributed almost uniformly and with enormous potential energy stored in the dense, hot conditions of the early universe. As the universe expanded and cooled, this energy was released and converted into the structures we see today: stars, galaxies, planets, and life. But each step in this process increased the total entropy of the universe. Stars burn hydrogen, increasing entropy by converting ordered nuclear fuel into disordered heat and light. Life increases entropy by consuming energy gradients and producing waste heat. Even the formation of galaxies and planetary systems, while creating local order, increases the total entropy of the universe when you account for all the heat and radiation released in the process. Entropy increase is inevitable. It's not something that can be prevented or reversed, not in the universe as a whole. Local decreases in entropy are possible. That's how complex structures like life can exist. But these local decreases are always paid for by larger increases elsewhere. The net result is always increasing entropy. As entropy increases, the universe becomes more disordered, with energy spreading out and becoming less useful. Eventually, in the far future, entropy will reach its maximum possible value. This state is called heat death, or thermodynamic equilibrium. In heat death, energy is distributed uniformly throughout space, with no gradients, no differences in temperature or density, no usable energy remaining. Nothing can happen in a state of maximum entropy because all processes require energy gradients, require differences between regions that can drive change. At maximum entropy, everything is the same, perfectly uniform, perfectly still, perfectly dead. The timeline for heat death depends on several factors, including the nature of dark energy and the rate of proton decay. If dark energy remains constant, as current observations suggest, the universe will expand forever, with the expansion rate gradually increasing. This accelerating expansion will eventually tear apart all gravitationally bound structures. Galaxy clusters will dissolve as their member galaxies are carried away from each other. Eventually, individual galaxies will be torn apart, then star systems, then planets, and finally atoms themselves if the acceleration continues to increase without bound, a scenario called the Big Rip. But current evidence doesn't support the Big Rip. It seems more likely that dark energy will remain roughly constant, leading to a gentler but still inevitable path toward heat death. Under this scenario, the universe continues expanding forever. Star formation ceases after about 100 trillion years, when all the available gas has been used up or dispersed. The last stars fade after another 10 to 100 trillion years. Stellar remnants, white dwarfs, neutron stars, and black holes dominate the cosmos. If protons are stable, these remnants persist essentially forever. But some theories predict that protons eventually decay with half-lives of perhaps 10 to the power of 36 years or longer. If proton decay occurs, even white dwarfs and neutron stars will gradually evaporate over unimaginable timescales as their constituent protons decay into lighter particles and energy. After perhaps 10 to the power of 40 years, all matter composed of protons would have decayed, leaving behind only black holes, electrons, positrons, neutrinos, and photons. Black holes would then be the dominant structures, but they too are temporary. Hawking radiation causes black holes to slowly evaporate. A black hole with the mass of the Sun would take about 10 to the power of 67 years to evaporate completely. Supermassive black holes like Sagittarius A star would take much longer, perhaps 10 to the power of 100 years or more. But eventually all black holes would evaporate, leaving behind only elementary particles and radiation. After about 10 to the power of 100 to 10 to the power of 110 years, depending on assumptions about proton decay and the masses of the largest black holes, the universe would consist only of a dilute soup of photons, neutrinos, electrons and positrons, all spread across an ever-expanding space, cooled to temperatures approaching absolute zero. This is heat death, the final state of the universe according to our current understanding. No structure remains, no stars shine, no galaxies exist, no planets orbit, no life persists. Just an infinite volume of space containing a thin mist of elementary particles and radiation, all at nearly uniform temperature, all at nearly maximum entropy. Nothing happens in this state because there are no energy gradients to drive processes. Time becomes meaningless because no changes occur to mark its passage. The universe reaches a state of perfect equilibrium and remains there forever, unchanging, empty, dead. This vision of the far future is profoundly nihilistic. It suggests that everything we see, all the beauty and complexity of the cosmos, all the stars and galaxies, all life and intelligence that has existed or will exist, all of it is temporary, destined to be erased by entropy over timescales that dwarf the current age of the universe. The cosmic story has a definite ending, and that ending is darkness and silence. Some find this vision depressing. If everything ends in heat death, if all structure is temporary and all existence is ultimately meaningless in the face of entropy's inevitable victory, then what's the point of any of it? Why does anything matter if it all ends in darkness? These are deep questions that science cannot answer because they involve values and meanings that lie outside the purview of physics. Science can describe what will happen to the universe, but it cannot tell you whether you should care or what you should make of this knowledge. One response is to embrace the temporary nature of existence. If everything is temporary, then the present moment becomes more precious, not less. If the universe is destined to end in cold darkness, then the fact that it's currently filled with light and warmth and complexity is more remarkable, not less. We exist in a special time, an era when the universe is capable of supporting life and consciousness. This era won't last forever. Eventually it will end, and the cosmos will enter a long twilight period before fading into darkness. But that eventual ending doesn't diminish the present moment. If anything, it highlights the preciousness and improbability of existence. We're fortunate to exist at all, to inhabit a universe that is young enough and structured enough to support life. The fact that this won't last forever doesn't make it less valuable. It makes it more remarkable. Another response is to note that our predictions about the far future are based on current understanding, and that understanding might be incomplete or wrong. We've been surprised before by cosmic discoveries. Dark energy itself was a surprise, discovered only in the 1990s. Before that, cosmologists debated whether the universe would expand forever or eventually recollapse in a big crunch. The discovery of accelerating expansion settled that debate while opening up new mysteries about what dark energy is and how it behaves. Similarly, our predictions about heat death assume that our current theories remain valid over enormous timescales, but we don't know whether this is true. New physics might emerge that changes the cosmic story. Perhaps entropy doesn't increase forever. Perhaps the universe undergoes cyclic behaviour, with periods of expansion followed by contraction and new big bangs, creating an eternally cycling cosmos. Perhaps quantum effects allow the spontaneous formation of new universes from quantum vacuum fluctuations, creating a multiverse where our universe's heat death is just a local event within a larger structure that continues indefinitely. These ideas are speculative, lacking empirical support, but they remind us that we shouldn't be overconfident about the far future. Our knowledge of physics is incomplete. We don't understand dark energy or dark matter. We lack a theory of quantum gravity. We don't know if protons decay, or if our current theories of particle physics are correct at all energy scales. Given these gaps in our understanding, predictions about the universe's fate trillions of years from now should be taken as provisional, representing our best current guess rather than certain knowledge. The universe has surprised us before and will likely surprise us again. Perhaps the far future won't be cold and dark. Perhaps something we haven't imagined will happen, some new phenomenon or process that changes the cosmic trajectory. We simply don't know. But even if heat death is the true ultimate fate of the universe, even if entropy inevitably increases until all structure is erased, the journey matters. The universe exists now, filled with stars and galaxies and planets and life. Consciousness has emerged, allowing the cosmos to know itself. These facts remain true regardless of what happens in the far future. The cosmic story, even if it has a definite ending, is worth experiencing and worth understanding. You exist now, in this moment, part of a universe that is vast and ancient and filled with wonders. That existence is meaningful not because it lasts forever, but because it happens at all, because matter and energy have organized themselves into patterns complex enough to think and feel and wonder. The universe has produced something extraordinary in you and in every other conscious being. That's not diminished by eventual heat death. It's a remarkable achievement regardless of how the story ends. The journey through deep time, contemplating the universe's evolution from the Big Bang through the current era and into the far future, creates a sense of perspective that's difficult to capture in words. Human life is brief, a few decades against the backdrop of cosmic time. Human history is short, a few thousand years of recorded civilization against the 13.8 billion year age of the universe. All of human existence is a tiny blip in cosmic history, barely noticeable on the timeline of the universe. Yet despite this brevity, despite how small and temporary we are, we're part of the cosmic story. We're made of atoms forged in stars. We're products of billions of years of cosmic and biological evolution. We carry within us the history of the universe, encoded in our bodies and our minds. You are, quite literally, the universe experiencing itself, matter that has become self-aware and capable of contemplating its own existence. This perspective can be vertiginous, dizzying in its scope. It's difficult to hold in mind simultaneously the vast scales of space and time and the intimate immediate reality of your own existence. How can you be both cosmically insignificant and profoundly meaningful? How can your life matter when you're just one organism on one planet, orbiting one star among hundreds of billions in one galaxy among trillions? The apparent paradox resolves when you realize that significance and meaning are not properties of the universe, but properties of conscious experience. Meaning emerges from awareness, from the capacity to value and to care. You matter because you're aware that you matter, because you can experience meaning and create it through your choices and relationships. The universe doesn't need to validate your significance. Your significance is a fact of your conscious experience, not something granted by cosmic scales or eternal duration. Living with cosmic perspective is an ongoing practice rather than a single realization. It's easy to lose sight of cosmic scales when dealing with everyday concerns, work deadlines, relationship problems, financial stress. These immediate issues naturally dominate attention because they're relevant to your survival and well-being. But occasionally stepping back and contemplating cosmic scales can be valuable. It reminds you that most of the things you worry about are temporary and local. It provides perspective on what might actually matter in the long run. It connects you to something larger than yourself, the vast cosmic story of which you're a tiny part. This connection can be comforting, a reminder that you're not separate from the universe but embedded within it. Part of an unbroken chain of causation stretching back to the Big Bang and forward into an uncertain future. Some people find cosmic perspective depressing, feeling diminished by the universe's vastness. Others find it liberating, feeling freed from petty concerns by the realization of how small those concerns are in cosmic terms. Both reactions are valid. The universe is large enough to contain multitudes of meanings and perspectives. How you relate to cosmic scales is a personal matter, dependent on your values, your temperament, your life experiences. There's no objectively correct emotional response to learning that you're a temporary arrangement of atoms on a small planet orbiting an average star in an ordinary galaxy. You feel however you feel, and that feeling is part of the human experience of grappling with cosmic knowledge. What's undeniable is that we live in an extraordinary time for cosmology. We've learned more about the universe in the past century than in all of previous human history. We've discovered that the universe is expanding, that it began with a big bang, that it's filled with dark matter and dark energy we don't understand. We've observed gravitational waves from colliding black holes. We've detected planets around other stars and found that planetary systems are common. We've mapped the cosmic microwave background and traced the evolution of cosmic structure from the early universe to the present. We've sent robotic spacecraft to explore every planet in our solar system and beyond. We've built telescopes capable of observing galaxies billions of light years away. The accumulation of cosmic knowledge has been staggering, transforming our understanding of our place in the universe. Yet for all this knowledge, the universe remains fundamentally mysterious. We don't know what dark matter is. We don't know what dark energy is. We don't know if there's life elsewhere in the universe. We don't know what happened before the Big Bang or if that question even makes sense. We don't know if there are other universes beyond our own. We don't know what consciousness is or how it emerges from matter. We don't know if the laws of physics we've discovered are universal, or if they're just local rules that happen to apply in our cosmic neighborhood. Every answer raises new questions. Every discovery reveals new mysteries. The universe is like an onion with infinite layers. The more we peel away, the more layers we discover beneath. This ongoing mystery is part of what makes science compelling. If we understood everything, If all questions were answered, science would be finished. But we're nowhere near that point. We're still in the early stages of understanding the cosmos. Future discoveries will surely surprise us, revealing aspects of reality we haven't imagined. Perhaps we'll discover that dark matter is something entirely unexpected. Perhaps we'll find life on Mars or in the oceans of Europa or on planets around other stars. Perhaps we'll detect signals from extraterrestrial civilizations or discover that we're alone in the universe. Perhaps we'll develop a theory of quantum gravity that explains what happens at the centers of black holes and during the Big Bang. Perhaps we'll discover that the universe is even stranger than current theories suggest, that there are dimensions or forces or phenomena we haven't detected yet. The universe's capacity to surprise us is built into the process of science. We observe, we hypothesize, we test, we revise our understanding. Each cycle of this process brings us closer to truth, but it also reveals how much we still don't know. The scientific project is open-ended, always incomplete, always provisional. Our current understanding is the best we have, but it's not final. It will be superseded by better understanding as new evidence accumulates and new theories are developed. This doesn't mean our current knowledge is worthless. It means it's an approximation, a useful description of reality that works within certain domains but might fail outside those domains. Newton's laws of motion are still useful for everyday calculations, even though they've been superseded by relativity and quantum mechanics. Similarly, our current cosmological understanding is useful and will remain useful even as it's refined and extended by future discoveries. Living in a universe that's fundamentally mysterious might feel uncomfortable. Humans crave certainty, clear answers, definitive knowledge. But the universe doesn't owe us certainty. It simply is what it is, operating according to its own rules regardless of whether we understand them. Our task is not to demand certainty from the cosmos, but to explore it with humility and wonder, accepting that some questions might not have answers and that some answers might be forever beyond our reach. The universe is under no obligation to make sense to us. The fact that we've understood as much as we have is already remarkable, a testament to human curiosity and ingenuity. Every piece of cosmic knowledge we've gained has required tremendous effort, centuries of observation, experimentation, and theoretical work. The fact that we've gotten this far, that we've mapped the cosmic microwave background and detected gravitational waves and discovered exoplanets, is extraordinary. And we're not done. The scientific project continues, driven by curiosity about the universe and our place within it. As we drift toward the conclusion of this extended exploration, the narrative naturally slows, becoming more contemplative, more accepting of cosmic mysteries. The universe is filled with scary places, yes, with black holes and voids and violent phenomena, but it's also filled with beauty, with structure and complexity that shouldn't exist according to the most straightforward extrapolations from the early universe's nearly uniform conditions. Somehow, despite the odds, despite entropy's inexorable increase, the universe has created and sustained complex structures for billions of years. Stars formed and created heavy elements. Planets formed and provided stable environments. Life emerged and evolved. Consciousness arose. All of this happened not through design or purpose, but through the working out of natural law over time. That's more remarkable than any designed universe could be. It means that the laws of physics themselves are creative, capable of producing outcomes as complex and interesting as life and intelligence, without any guiding hand or predetermined plan. You're evidence of the universe's creativity, a walking example of what matter can become when given enough time and the right conditions. Every thought you have, every feeling you experience, every moment of awareness, these are all cosmic phenomena, just as much a part of the universe as stars and galaxies. Consciousness is not separate from the physical universe. It's an emergent property of certain arrangements of matter, a pattern that arises when neural networks reach sufficient complexity. This doesn't diminish consciousness. If anything, it makes it more remarkable. The universe has produced something capable of wondering about the universe, matter that can contemplate its own existence and ask questions about meaning and purpose. That's extraordinary regardless of how it came about. The scariest places in the universe, from black holes to cosmic voids to the heat death awaiting in the far future, are all part of the same cosmic story that produced you. They're not separate threats existing outside the normal order of things. They're natural consequences of the same physical laws that allow stars to shine and life to exist. The universe is simultaneously dangerous and nurturing, hostile and hospitable, filled with violence and creativity. Both aspects are real and necessary. Without stellar explosions, there would be no heavy elements and no rocky planets. Without black holes, galaxies might not have formed efficiently. Without the vastness of space and the speed of a light limit, we might not have the isolation necessary for complex evolution. The scary aspects of the universe are often intertwined with the aspects that make existence possible. This intertwining of danger and possibility is characteristic of complex systems. Life itself is a precarious balance, sustained by constant energy flow and kept far from thermodynamic equilibrium. The same processes that sustain life also threaten it. Metabolism produces harmful byproducts. Evolution requires death and selection. Consciousness brings awareness of mortality. Complexity is inherently vulnerable, requiring precise conditions to persist. Yet despite this vulnerability, complex systems have proven remarkably robust, adapting to changing conditions, finding new ways to persist even as environments shift. Life on Earth has survived for nearly 4 billion years through multiple mass extinctions and dramatic climate changes. It's adapted to extreme environments from deep ocean vents to Antarctic ice. It's diversified into millions of species occupying countless ecological niches. This robustness in the face of danger suggests that life and complexity are more resilient than they might appear, capable of persisting through cosmic dangers that would seem insurmountable. Perhaps the same will be true on cosmic scales. Perhaps life exists throughout the universe, adapting to local conditions, persisting despite cosmic dangers, finding ways to survive in environments we would consider hostile. Perhaps intelligence is common, arising wherever conditions permit, creating countless civilizations scattered across the cosmos. Or perhaps we're unique, the only conscious observers in a vast unconscious universe. Either possibility is profound. If we're not alone, then the universe is richer and more interesting than we imagine, filled with other minds grappling with the same cosmic questions. If we are alone, then consciousness is even more precious, a rare emergence that might not occur again for billions of years, making our existence and our efforts to understand the cosmos all the more significant. We don't know which is true. The search for extraterrestrial life continues, with no definitive detections yet despite decades of searching. This silence might mean life is rare. It might mean intelligence is rare even if simple life is common. It might mean that technological civilizations are short-lived, burning out quickly after discovering technologies capable of destroying themselves. Or it might simply mean we haven't looked carefully enough, that life exists, but we haven't detected it yet because space is vast and our searches have covered only a tiny fraction of possible locations and frequencies. The Fermi paradox, the apparent contradiction between the high probability of extraterrestrial life and the lack of evidence for it, remains unresolved. Multiple explanations have been proposed, from the Great Filter hypothesis suggesting that something prevents most life from reaching technological sophistication, to the zoo hypothesis suggesting that advanced civilizations deliberately avoid contact with us. Each explanation raises as many questions as it answers. What's clear is that life as we know it requires specific conditions: liquid water, carbon-based chemistry, sources of energy, stable environments lasting long enough for evolution to occur. These conditions are common in the universe, but not ubiquitous. Many planets are too hot or too cold, too close to their stars or too far away. Many star systems are unstable or subject to high radiation levels. Many regions of galaxies are inhospitable due to high stellar densities or proximity to violent phenomena. Yet even accounting for these constraints, the universe contains billions of potentially habitable planets. The question is not whether habitable environments exist, but whether life actually arises in those environments, and, if it does, whether it evolves intelligence and technology. We have one data point, Earth, which is insufficient for drawing general conclusions. Until we find life elsewhere or definitively determine that we're alone, the question remains open, a source of ongoing speculation and a driver of continued exploration. The search for life has expanded in recent years with the discovery of potentially habitable exoplanets and the exploration of our own solar system. Mars might harbour subsurface microbial life. Europa and Enceladus have subsurface oceans that could potentially support life. Titan has complex organic chemistry and liquid methane lakes. Each of these locations is a potential habitat, a place where life might exist in forms adapted to local conditions. Future missions will explore these locations more thoroughly, searching for biosignatures or even direct evidence of living organisms. If life is found in our own solar system, even simple microbial life, it would revolutionize our understanding of how common life is. Two independent origins of life in one solar system would suggest that life arises readily, wherever conditions permit, implying that the universe is teeming with life. Alternatively, if life on other solar system bodies is found to be related to Earth life, perhaps delivered through meteorite impacts, it would suggest that life can spread between worlds, creating the possibility of panspermia on galactic scales. The implications of finding extraterrestrial life would be profound. It would answer one of the oldest questions in human history: are we alone? It would provide a second example of how life works, allowing us to see which features are universal and which are contingent on Earth's particular history. It would potentially offer new insights into the origin of life and the possibilities for different biochemistries, and it would change our perspective on our place in the universe, confirming that we're part of a larger community of living things rather than singular anomalies. Even if the life discovered is only microbes, it would be significant. If microbes are found on multiple solar system bodies, it would suggest that simple life is common and that the galaxy might be filled with simple organisms even if complex intelligence is rare. But even without finding extraterrestrial life, the search itself is valuable. It forces us to think carefully about what life is and what conditions it requires. It drives technological development as we build better instruments and spacecraft. It inspires wonder and curiosity about the cosmos, and it keeps alive the possibility that we might one day encounter other minds, other consciousnesses grappling with their own existence in their own corners of the universe. The search continues, driven by the same curiosity that has always driven human exploration, the desire to know what's out there beyond our immediate experience. Whether we ultimately find life elsewhere or discover that we're alone, the search will have been worthwhile, teaching us about the universe and ourselves in equal measure. As this exploration winds toward its end, the tone shifts from urgent discovery to quiet contemplation. The universe is vast, filled with wonders and dangers in equal measure. We've journeyed through 33 of the scariest places the cosmos has to offer, from voids to black holes to the eventual heat death. Each of these places reveals something about the nature of reality, about the laws of physics pushed to their limits, about the universe's capacity for both creation and destruction. They're terrifying not because they're evil or malevolent, but because they're indifferent, operating according to natural law without regard for life or consciousness or our human concerns. The universe doesn't care whether we exist, whether we thrive or perish, whether we understand it or remain ignorant. It simply exists, unfolding according to mathematical principles we've barely begun to comprehend. Yet this indifference is not something to fear, but something to accept. The universe's indifference means we're free to create our own meanings, to decide for ourselves what matters and what we value. We're not bound by cosmic purpose or divine plan. We're free to chart our own courses, individually and collectively, defining success and failure on our own terms. This freedom comes with responsibility. If there's no cosmic purpose, then we must create purpose through our choices. If the universe doesn't care about us, then we must care about each other. If existence is temporary and meaning is not inherent, then we must make the most of the time we have finding or creating meaning in our relationships, our works, our understanding of the cosmos. This is not depressing, but liberating. You're free to decide what your life means and what you'll do with the time you have. The universe will continue long after you're gone. Stars will keep burning, galaxies will keep colliding, black holes will keep consuming matter. The cosmic story will unfold over trillions of years according to the laws of physics, indifferent to human concerns. But right now, in this moment, you exist, you're aware, and you're part of that cosmic story. Your atoms will return to the cosmos when you die, perhaps eventually finding their way into new stars, new planets, new forms of life in the distant future. You're literally made of star stuff, and you will return to star stuff when you die. This cycle of matter through the universe, being organized into complex structures before dissolving back into simpler forms, is part of the grand cosmic pattern. You're a temporary eddy in the flow of matter and energy through the universe, a brief moment when atoms organize themselves into a pattern capable of awareness and thought. That's remarkable regardless of how temporary it is. Sleep now, if you're listening to these words as part of your nighttime routine. Let the cosmic perspective wash over you. Let the vastness of space and time put your immediate concerns in proportion. The universe is immense, ancient, filled with wonders beyond imagination. You are part of it, connected to everything through chains of causation stretching back to the Big Bang. You're made of atoms forged in stars, organized through billions of years of evolution into a being capable of contemplating the cosmos. That's extraordinary. That's worthy of wonder. That's enough, regardless of what happens in the far future, regardless of heat death or cosmic isolation, or any of the other scary aspects of the universe we've explored. You exist now, in this moment, and that's remarkable simply because it's so unlikely. Rest well, knowing that you're part of something vast and ancient and beautiful. The universe is scary, yes, but it's also magnificent, and you're fortunate to exist within it, to experience it, to wonder about it. Sleep, and let the cosmic silence embrace you. The universe continues its slow unfolding, stars burning, galaxies spinning, entropy gradually increasing, all of it proceeding according to natural law, all of it indifferent to human concerns, but also somehow producing moments of awareness and beauty and meaning. You are one of those moments. Rest in that knowledge. The universe is vast, but you are real, and that's enough.